Thanks for joining and thanks for being here at 10. I hope that more people will arrive as time goes by. And the point of today's session is to basically we want to showcase new results that have happened in 1 year, but also this is the 10th year of AIP. AIP started in 2016. So it's almost ending now this year. And we want to also summarize what we have achieved in the last 10 years. So I'll basically, in the first 30 minutes, talk about the summary and overview of everything that has happened, maybe most important thing. And then afterwards, we'll have some talks talking about new results that have happened in the last 1 year. Yeah, so we started the group actually. I was really the first employee of AIP, and this office didn't exist actually when I joined. And this office started in January 2017. It used to be much smaller, and our team used to be called Approximate Bayesian Inference at that time. And I wanted to have AI in the title, but at that time it was not allowed to have AI. But 10 years later, things have changed, and we have been officially allowed to change the title of our group to this title. So we, starting from July 1st, actually, officially, we'll be in like 4 days, we'll be Adaptive Bayesian Intelligence Team, and that's what we'll be called from now on. And I think the stuff that we've been doing for a year, actually, it's I always believe that this is a line parallel to what people call artificial general intelligence. So now I see the world being more ready for adaptation. So that's why I say AGI is meeting ABI finally after many, many years of exploration around this topic. So the AIP project has been going on, and in between, almost 3-4 years ago, we got a lot of funding to form this additional project, the Bayes-Duality project. That's what is like funding part of this workshop, focusing on AI that learns adaptively, robustly, and continuously like humans. The current team, it's probably not the most updated version, but we have lots of members, and we are a very diverse group of people. We are, I mean, a lot of German people show up, but other than that, there are people from all over the world. Like we have people from Latin America, we have people from Korea and other places. So it's a very diverse and dynamic group of people that have been joining us. So this is the list of people who have actually spent some time here. Most of them have spent like 6 months or to a year and more. And it's about 77 people now. And in the red, what I show is the new people that actually joined us since last year and now have left. Right? So this is the list of alumni. We've become so many people that we are actually doing our alumni gathering at every conference that happens. So it's quite nice to see people spend time here and go on to, do other interesting things, and then come back and meet with each other and still share some common research themes that we have been pushing people for. So just going back, right? Like, I think since the beginning of my research career, I have been fascinated with the ability of people to be able to quickly adapt and continue to acquire new skills throughout their life. And I want intelligent system to be like that. And when I was talking about this 10 years ago, so this video I think I show all the time, and this video is really taken 10 years ago because my daughter is now little about 10. And at that time when I was talking about this, and I showed this for the first time in 2015 in my when I used to teach at EPFL, showing what's the goal of machine learning. The goal of machine learning is to design machines that can actually do what people do all the time, every day, right? We are kind of making sense of, like, from random exploration of the world, we're making sense of things after we converge and we figured some things out, right? So this is very this is a video that maybe some of you have seen again and again and again, but it's kind of not gotten old for me. Like 10 years ago when I talked about this problem, we used to call it sequential information processing problem. Like, how do people learn process information sequentially when it's presented to them? And at that time, people, were, of course, people were busy in scaling things up, and people said, oh, SGD also does this, right? And it was kind of hard, and we had to invent words like, oh, this is bulk learning. We don't want all the data to be there at once. And this is kind of what I was selling when I actually started my position here. And thanks to Razwan and colleagues, that they came up with a very catchy term for this. Okay, yeah, you can explain the better story later on, but I thank you because you're here. So they coined the term continual learning, and I think somebody from Cambridge was visiting me in 2017, and they told me about it, and I said, oh wow, that's the right word. I'm going to use that word from now on. So we talk about continual learning, but really what we want is continuous adaptation for a very long period of time. Even though we don't have the goal and objective specified very concretely, right? And people are really amazing at this. So I'm always showing this, like this adaptation that my daughter is doing. But what I'm actually really fascinated with is, is how this knowledge is being transferred over time. And not only this, over kind of between people, right? So this is a new video that I took this year. Now I have another intelligent machine that's trying to learn. It's my 2-year-old son. And now they're collaborating and communicating. She's trying to teach him how to jump. And they're having a lot of fun in this communication and learning, from each other, right? I think communication is something that is very, very important in information processing, something that is completely missing right now in intelligent system. And today, I think I'm very happy to say that we'll talk a lot about communication. So lots of things coming that have happened in the last 1 year that help us kind of precisely write down how to do this sort of communication, the transfer between people and over time for a long period of time or between a lot of people. Okay, going back to, right, so people have actually been working on doing lots of amazing things with machine learning, right? We have amazing systems right now, but they're nowhere close to what we see in kids, the adaptivity, the fluidity of learning that we see in people and in animal of all sorts. Machine learning systems are very brittle, they're very bulky, they cannot adapt if something small is changed. And this is not really a machine learning system, but it's just to make you think what happens, right? When something is changed in the system very little bit, you're forced to retrain from scratch. And this is really like, I think I don't have to convince you. You can kind of imagine yourself that if you have a really, really large system and you have to always update it all the time, it's going to be very, very costly, right? And because it's costly, it allows only a few people to be able to do that. People who have lots of data, people who have lots of compute, they can afford to process all of that data at once. And this leads to inherently undemocratic system. It leads to systems that are unsustainable, that was just kind of bad for the world, right? So my solution to this is that we need to bring adaptivity, instill adaptivity into our systems, and that's the way forward, is what I believe. Whether it's the right thing to do or not is something that I'm still trying to learn more about and try to talk to more people about it to understand if this is what we should be aiming for. But many people have actually argued in favor of this, and there's lots of work that I found by some psychologists. I don't know if Joe, you know about this person, but this is quite amazing read if you go and look for adaptive intelligence. Many times actually it seems to be that it's very much the definition of how intelligence works, right? Of course, there is, even psychologists haven't come up with a coherent and consistent definition of intelligence, but it is very clear that adaptivity lies at the heart of it. It is a big part of it because maybe the goal of intelligence is not to do something, but it's just to adapt to what is being presented to it, right? That's one way to kind of think about it. And when we say we want adaptivity in our intelligent system, the question that we are asking is, how do these natural brains that we see in the world, how do they adapt so quickly, right? And in that question, as a machine learning person, I pose this question as, what kind of objective are they optimizing? Right? This is not really clear. Are these brains, they're optimizing some kind of empirical risk that we use in machine learning? And how are they optimizing it? Is it by backpropagation that such an objective is being optimized, right? In old times, we used to say that it's going to be something like a Bayesian objective. It's a Bayesian model. The brain is Bayesian, and we are basically using message passing in the brain, right? And that hasn't worked very well. And now what we do works quite well, but we still see that there is no adaptivity in the system that we see in the natural system. Right? So this is the question that I have been wanting to answer for many years, right? And I'm very happy with what we have achieved in the last 10 years, is that the hypothesis that I had in the beginning of this group that we formed here is that can we say that adaptivity is adaptivity necessarily involve something like a Bayesian computation? And I believe that we have been able to actually convince ourselves, at least I've been able to convince myself, that every time if I see that an intelligent system is trying to process information in an adaptive way, it has to necessarily have a flavor of a Bayesian computation. So something like Bayes' rule. And maybe it's not exactly Shannon entropy, maybe some other entropy that's being used. But the flavor of the algorithm is very similar. So perhaps you disagree with me, and it is okay, but I've convinced myself, and I will try to communicate that to you for the rest of my life. So part one that I will very quickly go through for just 10 minutes is to talk about this old work that we did, which really forms the basis of everything that has happened in the last 10 years in this group, is Bayesian learning rule. Essentially, it is a foundational way to derive learning algorithms, to think about what learning algorithms, what kind of objective they optimize. Well, it's a Bayesian objective, and how do they optimize it? It's a natural gradient descent algorithm. If you see it like that, then lots of things kind of naturally fall out of it, right? And then we have done a lot of empirical investigation on this to show that actually, if you use these principles in deep learning, it does lead to some improvement. It's not like 10% boost in performance, but the theory is very consistent, right? So Thomas and Nico will talk about this afterwards. And then I will take an hour to talk about my new work that I've been talking to people that, I've been working on this for 4 or 5 years. And I even gave a keynote at Colas last year. And I said, there is a Bayesian way to do it, but I haven't had time to write it down. So finally, it's out. And I actually think in a way that it's so this is a foundational way to derive adaptation algorithm. And in the paper, I argue that lots of algorithms in different kind of adaptation can all be seen as optimizing the same objective in a very similar way, right? So it actually, I think, gives very clear, not just hints, but clear road to how we can actually solve continual learning or adaptation. Okay, so I'll show some examples for continual learning, and then Siddharth and Thomas, they will talk about their version of federated learning. And because the work is so new, I think they will not say that they're doing posterior correction, but I'll correct them and tell you maybe later on in discussion, perhaps we could talk more that these are all just simply ways of actually correcting the posterior, okay? In the end, there will be more new work that has happened in deep learning. So Kenichi and Keigo, they'll talk about low precision training using Lie group Bayesian learning rule. So it's also a version of Bayesian learning rule. This paper just went on archive like 2 days ago. And then Songbai will talk about IVON LoRA. Okay, so some papers I've written here. But if you want to read two papers, it's the Bayesian learning rule and posterior correction. Those are the two things that summarize the 10 years of work that we have done. Okay? Okay, so I have 15 more minutes and I have too many things to cover, but I will just very briefly go into the Bayesian learning rule because I did this, if you were here on Monday, then we actually talked about it a little bit. About it, and also last year we did a little bit of tutorial on this. So hopefully I don't want to bore you with the old stuff, and then just do it very quickly. And then after this, after 15 minutes, everything that comes in is new that has happened in the last 1 year. Okay. Okay, I wanted to start by showing this quote that has kind of well, I should say that maybe this inspired me in the beginning of my research, but sadly I found this later on. But the work that we do in this group, that what inspires us is essentially this quote that was written by E.T. Jaynes in the discussion of this paper by Zellner. And the title of the paper is Optimal Information Processing and Bayes' Theorem. This paper actually shows, without using a Bayesian model, without using Bayesian inference, that if you want the information to be preserved, input information should be equal to output information, and necessarily that processing rule comes out to be a Bayes rule, the Bayes rule. Okay. And then in the discussion, E.T. Jaynes actually was very happy about it because it really directly connects to his maximum entropy principle. And he wrote this quote in the discussion, and you must read it. It's quite amusing, actually. The discussion by, there's also a discussion by Kullback, which is very funny because he says that this is incorrect. But yeah, okay. So he says that the fact that many different approaches point to the same actual algorithm is a major strength of Bayesianity. Okay, and this is kind of what we've been doing in this group. So we came up with this Bayesian learning rule, which is a learning rule that we use to derive all sorts of algorithms in fields like optimization, deep learning, approximate inference, and we also show that it's very, very closely related to things that are happening in global optimization. So this really goes along the line of what E.T. Jaynes actually was talking about. Actually, I just gave a keynote at BaseConf just last week in Singapore, and there was a student of E.T. Jaynes who was there at the talk, and he came and he said to me that he was very happy to hear about the things that I said in the talk. So I think I didn't say anything wrong, is what I'm saying. And he probably would have not been insulted if he was in the audience. So that's a plus. Okay. So just to start with this, and I just wanted to show that Bayes rule actually looks like this, right? I think most of you are familiar with theta is the parameter, and there's likelihoods, and you take the prior P0 and multiply and get the posterior P sub t. But we actually say that we should actually think about an approximate version of it that people called variational inference for many, many years. So you're trying to find the Q sub t that actually approximates the posterior, and you can write an elbow-like object, which you try to minimize to get that. And to make a connection to the frequentist world or the empirical risk minimization that's happening in the deep learning, you can actually denote some of these quantities in this way, and you can rewrite this objective in this way, where it looks more like the maximum entropy formulation. So essentially, the entropy comes from the relative entropy, which is KL, and I push the L0, which is the prior, to the first term. And so this looks a little bit more similar to what people actually know. And what we try to do is we try to use this formulation, variational formulation, to discover inherent Bayesian nature of non-Bayesian algorithm. What we chose then, the class of distributions, approximations that we should think of, we realized that exponential family is a reasonable class, and it's kind of sufficient to show all the results that we show. And I believe that the principles are actually a little bit more general. So the exponential families are these very nice class of distribution where if you take the log of them, then they are somehow linear in some sufficient statistics of the parameter. And lambda is the natural parameter. So its parameterization is quite important. And if you don't remember, the detail of this is basically some version of the mean and the precision matrix give you the lambda, and theta transpose is the sufficient statistic. So for Gaussian, it's quadratic. Right? We also realize that there is an alternate parameterization, which is a dual parameterization. It's another set of coordinate that people call expectation parameter. And it's the kind of this duality between the lambda and mu. So I write this here very precisely. Lambda is the natural parameter, mu is the expectation parameter. This duality is what helps us to derive the Bayesian learning rule. Okay, we'll show it very, very quickly. Most of you have probably seen this, and if you have not, it's time to read the most important paper from our group. Essentially, in deep learning, you minimize an empirical risk and you use an SGD style algorithm. We argue that more general thing to do is to minimize a variational objective. That's written in the right-hand side, right? So you're trying to now find, not find theta, but you're trying to find a distribution Q of theta, and I've written lambda to explicitly show the dependence on the natural parameter, okay? And the Bayesian learning rule says that we should use very similar algorithm here, but now it's written to optimize lambda instead of theta. So it's the parameter of the distribution, like the mean and the covariance, and we should scale by the Fisher, the gradient. And these are very special kind of gradients. They're called natural gradient. The important thing is that this Fisher doesn't depend on the loss. This is just a Fisher of the posterior. So it's kind of fundamentally different from it. Yet you can actually show that if you choose this algorithm, then you're able to derive SGD and ADAM and all of these algorithms as special cases of BLR by choosing specific exponential family. So by choosing specific natural parameter and the expectation parameter. Okay, and I got a lot of bashing from a lot of Bayesians because they're not used to writing it like this, because they don't kind of they're not big fan of convex duality perhaps. But if you go and talk to optimization people, they'll say it's just mirror descent. But then there is another problem that they say it's just mirror descent. You're not doing anything new. So get problem from all the people. Bayesians hate us, and then optimization people hate us, and then information geometry people come in and they say, oh, it's information geometric optimization. I know this. There's already a work that shows that lots of algorithms can be derived from this. Okay, so this was the battle that we fought for the last 10 years to tell people that actually, indeed, there's something very, very new here, right? And one fact that actually comes out is that you can rewrite this computation by using the gradient with respect to mu. It's very, very natural. And what we showed that computing the gradient with respect to mu is indeed a lot easier than computing the Fisher matrix and inverting it and doing all these calculations. You don't have to do it, okay? So a lot of work actually went into that. Essentially, well, I don't have time to show this, but if you want to compute like gradient descent, you say, oh, I'm going to start with Gaussian, where covariance is fixed. I will write down the natural parameter, expectation parameter, and then you write down the BLR, and you say, oh, entropy is constant. I'm going to plug in the natural parameter is M, expectation parameter is M2. So, oh, it almost looks like gradient descent now, right? So we're almost there. But then say, well, there's an expectation here. And I say, actually, expectation is kind of nice because this is the posterior averaging that Bayesians all love, right? So it's right there. And if you actually rewrite it slightly, so you push the gradient through the expectation, it's called Bonnet's theorem, then you see that posterior averaging is telling you that you shouldn't compute the gradient at one point, but you should compute at many points. Okay, you should sample from the distribution and then average it, right? But if you hate being Bayesian, that is fine. You can just approximate it at the mean. So gradient descent can be seen as finding the location parameter of a Gaussian. And if you interpret it like that, fine, Well, many people say, oh, you cheated. You did some weird approximation because you wanted to make it look like, gradient descent. To those people, I say, haters, back off, That's what I say, right? Because this principle can be applied for a lot of things, for a lot and lots of things, right? And lots of these algorithms like RMS prop, they're kind of, there's no derivation from it, right? They're just written in some hacky, lecture notes. And from there, people have actually applied these things and they work quite well. But here, actually, if you do the exact optimization of the variational objective, you get very, very similar algorithms. So Thomas will talk about this in a few minutes. I just wanted to tell you that this is not a coincidence, right? This expectation that I pushed inside, that people hated me for many, many years, especially in the UK. Yeah, because they don't like this, they like their probabilistic models with the prior and the likelihood. This doesn't do any of this, right? This kind of circumvents the problem, and it tries to build a direct bridge with deep learning folks to say, well, if you didn't do averaging, then you would be what you're doing. But maybe averaging has some advantages to it, right? So there is actually a very foundational thing here, and I've known about this since 2018 and even sometime before that, but I only start to talk about this recently because it kind of makes sense now in the current time. So why do we recover optimization algorithm? Because in gradient descent, you could see this as a surrogate, like a linear surrogate, right? That you're doing optimization on. In a Bayesian one, when you choose isotropic Gaussian, like for the Gaussian SGD result, that gradient descent result that I showed you before, you get an expectation. And it turns out that it's also a surrogate. Okay? You can write an equivalent problem with this surrogate that you minimize, okay? And this is over the mean now, that you're able to actually compute a new distribution, okay? So fundamentally, the surrogate is different. Here, the surrogate is obtained at old parameter, and here the surrogate is obtained by sampling from the distribution and then averaging the gradient. So so this is like a smooth surrogate. It doesn't actually end here. This is just the beginning of it, right? Now, if you go from an isotropic Gaussian, if you go to a full Gaussian, if you write down the surrogate for the Bayes, it's a direct generalization of the Taylor's quadratic approximation. Okay, so here you simply replace the gradient and the Hessian by the expected version of it. Okay, you can see the figure that's drawn there, but this never stops actually. You can start with you can take any arbitrary exponential family. Okay, you can do the same thing. This is an equality, actually. You can show that any distribution that you find by optimizing a variational objective has this form where you're linear with respect to t of theta, okay? So it's like linear here with respect to quadratic. And the gradients are replaced by the natural gradients. So actually these expectations that you see, these are just simply natural gradients. Okay, so it's not a trick that I push the expectation inside to make it look like that I'm doing something important. But it's a very fundamental thing. When you do a Bayesian approximation, it's actually a generalization of Taylor's approximation, right? You're optimizing a point, you get to a minimum, but now you're optimizing a variational objective and you get to a distribution. And that distribution gives you this kind of stable point where the function is approximated in this fashion. Okay, I've run out of time, but it turns out that so I go back now full circle. If you tell Bayesian that this is a site function, they'll probably be, this was my mistake maybe. I should just said that, oh, this is just a site function that you've already known all this time with your favorite expectation propagation, but this is a site function of a variational approximation. Okay, and it simply contains natural gradient, and that's the kind of is the result. And why it's important to talk about now, because site is how we do adaptation. So what I'm actually claiming that all sorts of adaptive algorithms, they're all using this site function to do adaptation, and it goes into the dual representation in the fashion that, sorry, I'll just take a minute and finish it. Essentially, you can just rewrite. So if I denote that site by L hat of the ith example at the qt, q sub t, then I could simply write my posterior as a factorized, version, which is represented in terms of the site. And this is also, sorry, so there's an equal arrow here. It's the same way you can write as lambda is made up of the natural gradient, okay? And to kind of tell people who were talking about sparsity yesterday, if you pay attention a little bit right now, this is is what sparsity is in the Bayesian sense. So Bayes is kind of sparse in the sense that natural gradients are additive. Okay, so it's a kind of a representer theorem because the larger natural gradients are more contributing to the solution, and the smaller natural gradients are contributing less. Okay, so it's actually encoding a kind of sparsity in the sense that the more important examples are represented more in the natural parameter or in the distribution through their side function or through their natural gradient. Okay, and in the second part of the talk, in maybe 1 hour, I will basically talk about how this dual representation helps us to do all sorts of adaptation. Okay, so this is where and maybe I could just show you like this, showing a visualization of these natural gradients. When you're close to the line, then they're quite big. When you're away from the line, they're small. Okay, you cannot see much in this screen, but the screen is pretty bad. So I'll end this here and then give it to the folks afterwards, and maybe we can do the questions afterwards, right? Yeah.
Yeah, so I will talk about a method called IVON, which is an implementation of the Bayesian learning rule that we've seen in the previous task for Gaussian distributions with diagonal covariance. And this leads to a very scalable deep learning optimizer that we've used now in the last year for many different projects. And in this talk, I will give an overview over many projects which use our method. So the IVON optimizer, actually, it's many people were involved. And on the photo on the left, you see this was the first Bayes-Duality workshop in, I think, in 2022. So there's a typo. This would be 22. 2023. Okay. And yeah, you can see the IVON first author at the blackboard doing the derivations and so on. So this was quite fun. So that was Yusong. And then
everybody's wearing the Japanese kimchi.
Yeah, so we went to the onsen and then we thought, okay, let's do some math. And eventually this led to a paper that we presented at ICML 2024 on this IVON optimizer, which is an implementation of the Bayesian learning rule for large neural networks. And as you can see, many people also came to the poster. There was quite a lot of interest in that work. And today I will talk about, so this was last year. Today I will talk about what has happened in 1 year. What have people done with this? Before I talk about the follow-up projects, a quick overview of IVON. Yeah, the projector is actually really bad. So this plot doesn't make any sense. Yeah, it's quite unfortunate, but what you're supposed to see is here kind of a logistic regression training, where in red you see an IVON-like optimizer. Wogen, this was a previous version. In blue, you see the Adam-style training. And there's very thin red lines, maybe you can spot them. And these thin red lines are samples from this probability distribution, the exponential family distribution, which kind of give you the uncertainty of the problem. So you can estimate regions where there is little data. So you get the weight uncertainty. And we can match the performance here on ImageNet and for training GPT-2. So this optimizer was the first variational method which could train large language models, or maybe GPT-2 is a tiny language model nowadays. But back then it was not the smallest one. So up to 1 billion parameters we could match or even improve the performance of ADMM. So the red curve is our optimizer. And most importantly, it's very easy to use. So it's just a few lines of PyTorch code, and you can use that Bayesian learning rule implementation. And it's more than just the uncertainty. So you will see that one can use this in a quite versatile fashion, that probability distribution that you get. In the original IVON paper, we did some sensitivity analysis also with the uncertainty, but we can also use it for knowledge reuse, like model merging or sharing, federated learning, which we will see later today. And the method is quite competitive with other Bayesian deep learning methods. So we won the NeurIPS challenge on approximate inference in deep learning, where the goal was to approximate a kind of a posterior computed on 512 TPUs using sampling, just with a budget that's not much larger than the SGD training. And the goal was to get as close as possible to that posterior. And IVON was the winning solution to that competition. And you can see that it matched other Bayesian methods such as the Swaroop method, or these are some sequential anchored ensemble method. So we got $3,000 for this, which was nice. And then, yeah, we already saw, so what is IVON actually optimizing? It's the objective that Emti presented in the previous talk. So instead of the standard objective that you would solve with ADAM, you solve the variational objective where you optimize over distribution. And this gives us a way to kind of characterize multiple solutions in a probability distribution. And yeah, I mean, if you're not familiar with this kind of learning problem, the difference is essentially that we want to find a probability distribution such that if we draw models from them, they should have low loss. So this is what the expected loss term is doing. And the entropy term says these models should be diverse. And that way you get many diverse solutions to the learning problem, which all have low loss, are a good fit. And as I mentioned before, and what you will see is that this distribution that you get on top with no overhead, on top of ADAM, if you use IVON, it will be useful in many different applications. This is the optimizer on top. That's the Bayesian learning rule in that lambda coordinate system that Emti had in the talk. And if you write out that very innocent looking equation in lambda, if you write that out in the natural parameters of the, yeah, I should use actually the mouse to point, because then people on Zoom can see it. If you write out the equation in lambda in the parameters of my Gaussian distribution, here M and H, I get an optimizer that looks very similar to RMS prop or ADAM. And the modifications that we have to do to RMS prop here, so I omitted the momentum, are highlighted in red. So basically in the first line, it's the same, except that you evaluate our parameter at a random sample from that Gaussian distribution. RMS prop uses a squared gradient estimator for the preconditioner. This is here more an unbiased estimator of the expected diagonal Hessian. That's why we call it a Newton method, because this is trying to estimate the Hessian matrix of the problem. Third line is exactly the same. Fourth line is also the same, except that we precondition with H rather than the square root of H. And then from this H vector, we can obtain the variance of our posterior just by a rescaling using the temperature that's there in the problem. We use a simple isotropic Gaussian prior because that's also what people use in deep learning, and this leads us here to this similar update in line 4. And in the end, we get our neural network as we like it, but instead of having a parameter, just a number for every connection, we actually have a Gaussian distribution, and we can draw random numbers from that Gaussian distribution, and we get many diverse models. So this is a quite faithful implementation of this Bayesian learning rule that we have seen in the previous talk, but in a way that it scales to large neural networks. And if you want to use it in PyTorch, you do pip install IVON, which installs the IVON package, which you then can import in Python. You remove your ADAM optimizer and use the IVON optimizer instead. And you add one extra line here, which does the random weight sampling. And if you want to do multiple samples, you can also add that for loop here. So this is the only change required. So it's very easy to try out. And yeah, indeed, many people downloaded that optimizer. So there's roughly 10,000 downloads now of that package. And people have used it in their research. And yeah, today I would like to show you what people have done with it. Yeah, 1 eternity later, 1 year later, what has happened. So yeah, one work that we did, this was more on the theoretical side. It was an intern here at RIKEN, Avrajit Ghosh. He wanted to understand why IVON works better. So we found it often improves the generalization in deep learning, and he wanted to understand why it works better. And there's a strong correlation and also theoretical reasons why flat minima in deep learning generalize better than sharp minima. And what one can observe is that if one trains with gradient descent with learning rate rho, the largest eigenvalue of the Hessian, which is here called the sharpness, hovers around the learning rate used to run gradient descent. So if I use a large learning rate in gradient descent, I find a minimum that's flatter than if I use a small learning rate. But what we observed is if we do variational learning, so here it's a variant of IVON where we actually fix the posterior covariance. If we fix the posterior covariance to 0.05, we find a much flatter minimum than gradient descent. And if we fix the variance to 0.1, it becomes even flatter. And
it's exactly the gradient descent that I showed with the expectation.
Exactly. So if you remove the expectation in Emtiyaz talk, you suddenly become much sharper, which is worse. So there's a good reason to be Bayesian, actually, in deep learning. And we wanted to understand, okay, why do we find a flatter minima? And Avrajit devised a theory which actually closely predicts. So this dashed line is a theoretical result similar to this 2 over rho of gradient descent. He modified that 2 over rho, and we found that his theory can predict actually the sharpness of the minimum if we train with IVON.
What problem is this?
This is training a reasonably big neural network on MNIST, I think here. So this is not GPT or anything, but it's still not a toy example. So how did he do this? So this analysis is called edge of stability. And the idea in edge of stability is to start with a quadratic loss. And basically on a quadratic loss, we descend, our gradient descent reduces the loss if the step size, if all eigenvalues are bounded by 2 over the step size. And he did the analysis of this noise injected gradient descent, which is IVON with a fixed variance, also on that quadratic. And he found that we get an expected descent in loss, also if our eigenvalues of the quadratic are bounded by 2 over rho, but you get this additional VF, so that's called variational factor, which depends on the number of posterior samples, on the posterior covariance, and some additional constants. And the intuition is that if we use many posterior samples, we can converge on that quadratic. But if we increase the posterior variance, the process gets more noisy. And if we use few samples to approximate the expectation with large variance, the process is very noisy. And the idea is that because you are noisy in that quadratic, the process escapes to a flatter quadratic where it's stable. So this is essentially moving you to a landscape in a non-convex landscape where your noisy process is somehow stable and the flat regions are stable. So this is kind of a theoretical analysis which people did for gradient descent, and we extended it for IVON and have some theoretical basis why the generalization of IVON is improved. We also did in another work with collaborators from Switzerland, we did a convergence analysis of IVON-like methods. I will not go so much into the detail here, but there's essentially a convergence proof in continuous time of that preconditioned gradient descent and a convergence proof in discrete time for a square root parameterization. So we have some theoretical basis that this, at least on convex objectives, this also can converge to the solution of the variational objective. Another theoretical analysis, which I was actually not part of, done by Sin Han, an intern here also, a tech staff in our team, and Emti, is that if you train with IVON, actually the noise in the posterior that we inject can be viewed as something like label smoothing, and not just any label smoothing. So what is label smoothing? We basically don't train on our labels Y, but we add a uniform distribution also on the labels. So it's instead of a 0 vector with a single 1, it's more like 0.1s and a 0.8 or something like that. And there's also adaptive label smoothing, which based on the input add noise to the labels. And there exists many heuristics for this adaptive label smoothing, which work quite well. But what this work shows is actually that if you train with IVON, implicitly you're already doing adaptive label smoothing, and the noise is data dependent. And there's few examples which do a lot of label smoothing, and many examples don't do that much smoothing. And the data points where there's a lot of label smoothing, we can also see there are more unusual data points than the low noise examples. So if you train with IVON, perhaps you don't need to tinker with your label smoothing. So this is another reason why the method can work well, because the smoothing methods have shown to improve the performance. Especially if we train with noisy labels, then actually we found that IVON works better than label smoothing, and also than a method called SAM, sharpens aware minimization, which is also a strong baseline for training with noisy labels. So on this plot, you can see the accuracy, on the x-axis the corruption into the labels, and IVON's performance degrades much more gracefully than the performance of label smoothing or SAM methods. And here it's plotted for a single class that the IVON's label smoothing in red matches previous hand-designed adaptive label smoothing methods in blue. Gives kind of a similar effect, but it's much easier to use. So this work also got actually the best paper honorable mention at ALBI recently. This is also a recent work which we hear by on Friday, actually by Marcus. He's in the audience, so he will give this talk. So they have used IVON for visual question answering in a computer vision setting. So I'm also not involved in the work, but I wanted to highlight because it's a really cool use of IVON. So the idea here is that we have an image and a question, and then we want to give an answer to that question. But if we are unsure, then we would rather not give an answer to the question, but rather say, okay, we abstain, we don't answer. And if we use IVON as a kind of training method, we can get uncertainties, and then based on these uncertainties, one can abstain. But you will hear much more on this on Friday, I think. But this was a cool application of IVON. Yeah, and then Nico recently had a work at iClear on using IVON for LLM decoding. So I will hand it over to him.
Thank you. Yeah, so in this work, we used IVON, as Thomas said, for LLM decoding to improve it. And in general, what people usually do in LLM decoding is they have some language model, which we denote by p theta. And they use usually two flavors of strategies for generating some output y given some input x here, which is either to sample the output y directly from the model or to try to find the most likely output y given that model and the input x. But these two strategies, they fail for various reasons. For example, one might sample a bad token during the generation, or which could lead, for example, to hallucinations, or more broadly, the most likely sequence y star that is found here might be most likely, but it might not correlate with what humans would think is a high quality output. For example, in a problem like machine translation, because there could be hallucinations or mistranslations, even though the sequence is likely under the model. So what people have done to improve over this is called minimum base risk decoding, which is this inner expectation here, where instead of just considering the most likely output or just one sample from the distribution, there's actually an expectation over all possible outputs that one could construct from this vocabulary V, and an expected utility here that compares all outputs y against the current output y prime, such that for each output y prime, we have this expected utility that tells us how good, for example, one would rate this output according to some quality criterion that is captured by you. And this already improves language generation because it captures this predictive uncertainty of the model, but it does not capture what we would understand maybe under weight uncertainty, and does not account for what different models might consider a likely output. So in this work, what we did is to extend this by this additional expectation over Q, which is just the approximate posterior, which we might get, for example, from IVON, such that actually we don't have only an expected utility over this model, but we also have an expected utility over the posterior. And all these kind of utilities are averaged out to consider different types of uncertainty. And what this would give us in theory, if we could calculate these expectations exactly, we would get the most or the best output according to this utility function U with the highest expected utility. But in practice, we cannot calculate these expectations exactly because the space V star is too large, and also we cannot consider all models that we could capture by Q. So in practice, what this gives us is a method where we would sample models from the posterior, then different outputs from the models, and we would average them to get this expected utility. This is also quite nice because even in the absence of some explicit posterior Q, we could use, for example, black box LLMs and ensemble them using this method. But what we mainly do in this work is using IVON to learn this posterior Q. And here we try this out on various tasks. So there are machine translation tasks, summarization, data to text, and regression tasks. And the crucial thing in these results is that both rows, which we see here in yellow, which use just a single model trained using ADMM and MBR decoding, and the red row, which uses samples from the IVON posterior, they have the same computational complexity, because here we consider 40 outputs for one model, and here we consider 4 models and 10 outputs, so there's no additional overhead when going from the yellow line to the red line. But even though we don't have overhead really in training, as Thomas has said also earlier, and we don't have any overhead in decoding, we still get quite large improvements for all these kinds of tasks. So for example, on this machine translation tasks, in terms of COMET, which is a quality estimation metric that is learned to show or indicate which quality humans would assign to a translation, we get improvements of 0.8 just by using the IVON posterior instead of using just one model trained with ADMM. So in summary, even for somewhat larger LLMs, now this is not the largest out and there are larger models, but here on Gamma with 2 billion parameters, when fine-tuning with IVON, we get a very practical method of improving decoding without really any overhead. And with this, I think I'm handing over to Thomas again.
Yes, so we did another work which Chongbai will present in the afternoon on fine-tuning with IVON. So we had a workshop paper at NeurIPS, and now we have a newer paper on arXiv, where we found that fine-tuning with IVON, LoRA fine-tuning with IVON can often give drastic improvements in accuracy. So sometimes 6% in accuracy improvements over ADMM, and also reduce the calibration. But I don't want to spoil too much here because there's a talk in the afternoon on this, but IVON also works well for LoRA fine-tuning of LLMs. Also this afternoon, Siddharth and I will give talks on using federated learning, IVON for federated learning. We have a new Bayesian federated learning method that we can plug IVON in, and it beat all the standard baselines for federated learning by a large margin. Yeah, then finally, this is not about IVON, but perhaps a little bit inspired by IVON. So IVON uses a Gaussian distribution for solving that Bayesian objective, but of course we can plug in other exponential families, other distributions. And in this work, we studied what happens when we do learning with log normal distributions. So these are on the positive numbers, these written here, the log normal distribution, and Keigo Nishida, in collaboration with the mathematical science team from the Bayes-Duality grant, worked on these kind of multiplicative updates, and we found that they give very strong results here for training large models on ImageNet and also for GPT-2 training, especially with the low precision, using low precision forward passes. And I think these connect also to the multiplicative updates that we have seen yesterday. Slightly different, but this is, I think, a nice study that IVON might not be the only variational learning method, but there could be interesting alternatives by changing the shape of the approximate posterior. And this highlights the generality of this framework, that many different algorithms can be derived from that rule. So yeah, that was everything that happened in the last year with IVON. And yeah, I'm happy to take any questions.
Any questions for Thomas, Nico?
Maybe this comes in more detail in the later talk, but the last slide, so what is why is it especially beneficial for this low precision scenario?
Because the noise is multiplicative, and you can imagine if you add a very small number to a big number, in low precision, nothing happens. But if you multiply, still something happens. So kind of addition is not so well suited for low precision training, and multiplication is much more natural in low precision setting. So both the noise injection and the gradient update is done via multiplication. This is simply because of the inaccuracy. Adding a small number to a big number in low precision has no effect, but the multiplication will still have effects.
It works in exponential, 10 raised to the power minus 10, minus 12, minus 13. So you have to add noise in that level to the exponent.
When I think, like, I know the answer to the question, but in the comparisons that you've done, like, did you try to take from Adam and then construct on the spot like a posterior by like a Laplace approximation, right? You take the square, and how that compares to what IVON does, right? In the papers, you always compare with Adam, just create a single model, but you can construct a distribution out of that.
Yes. Yeah, we compared here with various types of Laplace approximations. Okay. So these are better than, so the diagonal Laplace is better than just the Adams thing. Yeah. And then we found they don't give this boost in accuracy. Okay. So to avoid the overfitting with the noise injection, it can be quite important to do this be Bayesian during training and not only at the end.
Yeah, I think in all papers we have compared them to like Laplace style thing. And the Laplace style thing, the main issue is that you need to do a pass through the data to compute the Hessian or do something like that. I mean, IVON, you don't need that. And the other thing is that usually people use K-fac style thing, but here we're just using diagonal. And we still show that the diagonal one works better than doing K-fac. So I think that this is a complementary thing that you get by injecting noise. You improve things. It's for free, you know. So you could actually imagine that you do more complex posterior covariance, but you don't need to go there right now.
Thanks. This is super impressive. Thank you for sharing. I was wondering, do you find sometimes it, let's say, helpful also to maybe even make this noise adaptive in the sense that you change the amount of noise that you want to apply in the course of training? Is that kind of more help? Can that be depending on what you do exactly? I know you learn parts of that in some sense, right?
Yeah, so the noise is already adaptive. And sometimes this helps. So I must say the fixed noise is a strong baseline, but being adaptive gives a bit of extra boost in some situations.
I also want to add that it's not only helpful often to adapt the noise during training, but sometimes also when doing testing and during inference, because, for example, in the work that I showed, what we found out is that basically the improvements that we get from using IVON, they get bigger if the models that we sample from the posterior do different things. So also at test time, one can adapt this noise to sample from the posterior with different noise levels to, for example, promote diverse outputs, and then these improvements, they also get bigger. And I think Chong-Bai also has some results later on to show that varying this noise level during testing also helps with calibration, and it's not only during training. So during training, it's already adaptive, but during test time, one can also kind of tune this as a temperature parameter.
Yeah, so I've been working very, very hard, because I've been saying for the last 2 years that, oh, I've got it. Like I know how to solve all these things, and just it took a lot of time to put a document that I'll be happy with. It's still not submitted anywhere, but last week I gave a keynote at BaseConf about this. So then finally I had the reason to really push hard and get this out. So yeah, so as I said in the previous talk, that the goal is really to, what we really want in adaptive intelligence is that we want to understand how do these natural systems, natural or intelligent system, they can adapt quickly. And the main question there is that what are these intelligent system trying to optimize? What's the goal of adaptation? What is the objective that we should be optimizing, that we get adaptivity naturally out of it? And how should this optimization proceed? Okay. I think the posterior correction answers this question. And what I have kind of tried to do, and I'm not a theory person, so I don't prove stuff, but my style is more like maybe a person who does physics. Also, I'm not a physicist, but I try to show examples of the same concept in many different scenarios and try to convince myself that there are some principles that are universal, right? So I have kind of done some of this and I have some more ideas, but we'll talk about like continual learning, model merging, unlearning, influence estimation, student-teacher learning, federated learning. So I know that each topic requires its own kind of talk, but my hope is that I'll stick with continual learning and then I'll talk about how it's connected to other things briefly. And then in the afternoon, we'll have a full session on federated learning. Perhaps during that conversation, we can make something more concrete. And I think each task here has a new insight. So that's it's important for us to study adaptation, not in isolation of individual tasks, rather in its generality, because we start to see how these different methods, they're all different ways to correct the posterior, but they're actually bringing a new insight in how to correct it. Okay, so the hypothesis in this work is that all the adaptive intelligence system should be optimizing some kind of posterior correction. So their goal is to approximate the posterior using variational objective, but then to correct it because it was somehow not done it right, because it was approximate. It turns out that you get corrected exactly, but exact correction is too expensive. So different adaptation methods make different trade-offs to somehow solve that problem. Okay, so adaptation is not solved yet, but I think this is kind of a large jump in understanding how to solve it is what I'm trying to present to you. So let's go back to this variational formulation. And I'm going to talk about this kind of continual learning, online learning kind of setting. And Bayes' rule actually gives you a quite nice way to do this. It's really going back to optimal information processing by Zellner. That's how he was actually thinking about that. If you're given some information, then the output information is not destroyed, it's kind of preserved, and that has to be through Bayes' rule. The nice property of the Bayes' rule is that it can be written in a sequential way. So what I've actually done here, right? So I've said that the next posterior at time t+1 is basically equal to the previous posterior times times the loss function that you observe right now, the task that you observe, and you normalize, right? And if you repeat this, you'll be doing the optimal thing. Of course, under the assumption that there's a Bayesian model underlying. But you go to the online learning community and you'll see that there are very similar rules that are forms of Bayes update, specifically something called exponential weight update aggregate. They also do very similar things. So this is a general principle to think about it. Now, why these things don't actually work is because you can't compute the exact posterior, right? So what you say is that, oh, well, I'm going to do an approximation. And in the batch version, you write the approximation in this form, as I showed to you in the previous talk, that now the sum runs to t+1. Okay, and I've started with the prior, right? But this is not sequential. It's not written in the, so it's not a quick adaptation because I'm actually doing a full batch thing. If I want something that adapts quickly, I want it to be something like Bayes' rule, right? It should be recursive. So there's a version that people have used, and it's kind of very closely related to what EWC folks did, right? And this is, so you can actually derive EWC as a special case of this if you wanted to by using point estimates and Laplace approximation by ignoring these expectations. But we'll do the Bayesian version because it helps us to see the error that is being made. So if you wrote the variational version of this recursive rule, right, you would basically replace the prior by the posterior. Okay, this is clear, right? And now what I'm saying is that this is actually wrong. Okay, because you're doing approximation. So at every step you do approximation and then you do sequential update. It's not the same as doing everything at once and then doing that approximation, right? So it turns out that this is actually wrong, and you could convince yourself by thinking that if you actually added something and then you removed, you will not get back to the same place. You know, you'll be at a different place. So it's actually incorrect. So when I actually started my PhD, this used to be a big topic in approximate inference. People worked on state space model quite a lot with expectation propagation, where this sort of accumulation of approximation error was a thing that we wanted to solve. Of course, that kind of died down. It fell out of fashion, but I'm kind of bringing it back right now to say that my claim is that this is actually inaccurate. And if you start to ask this question, how inaccurate is this Q hat? Can we correct it to exactly recover QT plus 1? If you aim for this goal, I call this posterior correction. Now I'm saying that actually other hacky methods that people have devised, in which we think hacky, by the way, I'm not insulting them. These methods are actually a way to correct the posterior. They're actually indeed going for this rather than going for this. So I think Bayesian methods don't work for continual learning because we're actually aiming for the wrong thing. We're making these errors. And I'll show you specifically that these memory-based methods that people use, they're actually a way to correct the posterior, okay? So that's the claim, okay? So I'll essentially talk about continual learning, and I've written it in the distribution form, but you may as well replace this Q by a theta, right? You can have a theta t plus 1, theta t, theta t minus 1, theta t plus 1. And as I showed in the previous talk that I gave just in the morning, if you remove took the expectation inside, you will recover those frequentist version as a special case of this. So I'll work with the distribution version, and it's understood that the frequentist one, these results can be just translated to them by ignoring the expectation, okay? It doesn't increase the computation cost, it's just the way of thinking with the Bayes rule helps me to put all of these different ideas together. So for example, if you think about unlearning a concept, a data example or a data set, or understanding an influence of a data set, the adaptation looks like this. So essentially, you have your posterior. So you did some pre-training. So gray lines are showing you pre-training. And then you had a pre-trained model. And now you want to remove a data example or a set of them. Then you would kind of want to quickly adapt by doing this, right? So the thick arrows. So this is not a graphical model. It's just showing how the information is actually flowing. And to get this thing, you need the data set that you want to remove, and you need the pre-trained model, and you want to do it quickly, right? You don't want to, again, go back to the original data and do full retraining on it. Similarly, in model merging, you have an LLM, you fine-tuned 2 models on 2 different languages, perhaps, and now you want to use all of this to improve your LLM very quickly. So the thick arrows actually show you that you want this quickly. It is just a way to write quick adaptation. Okay, so it's an improved model Q+. In a similar way, I'm doing federated learning. So I want to learn jointly from the two data set, but I don't have access to it. And I get some local models trained on these data sets. And now I just want to quickly communicate with them to adjust my model. Okay, so at every step, I'm trying to do this in this fashion. Of course, federated learning, the goals are different, but you can think of this as like distributed learning in some sense, where you want to quickly adapt or reuse knowledge of other models and do something with it. Okay, we good with this? Okay. Okay, so what I'm going to show is that all of these things can be written as posterior correction. Okay, and then we'll see that different methods are trying to basically correct the posterior. Okay, I want to give you the main idea behind this, and if you really understood this slide, then you kind of understand. And then math is basically just 3 lines, so it's not that hard. Okay, so the main way to think about this is that when you're doing adaptation, you have to correct the past because there's a new data that's coming in, and it's interfering with how you viewed your past. Okay, so you want to correct the past due to the interference that is created by the future. Okay, you go into a different situation, now you have to reassess how you view the world. Okay, there's a simple example here that so here you cannot see, but this is a plus one class, and this is a circle class. And suppose I have an old model, so I call it OQT, but it's just a decision boundary specified perhaps by the mean of the Gaussian. Right, and maybe I got a new data set. So I got new data set. So there I got circles here now where I thought that there should be pluses, and I got more pluses here. And now my old model has to change here, right? So I have to move to be able to classify the data well. I have to move, right? I just want to show you what's happening, right? Old data. I didn't know what will happen here. I classified it as plus because it looks like this is like the biggest margin, right? It makes sense to do that. And now I suddenly got data here, circles, so I have to move my line to draw this here, right? I can still do a good job in classifying things. But what has actually happened, right? Previously, because my line was here, I was very safe about these data points. They're very far. I'm very sure about them, right? But now that I observe new thing, now these points in my past, now they're very close to my decision boundary, right? I'm not so sure about them anymore, right? So this is kind of what I'm calling interference. And interference is really as old as machine learning. The oldest paper that I've actually read, the word interference, is by Rick Sutton. Yeah, Charles Sutton is a different guy. Rick Sutton in 1986. He talks about this and backpropagation, how this interference is a problem. And I think reinforcement learning people normally think in terms of adaptation. So for them, this is actually a very common thing that when future has changed, it will interfere with something that has happened in the past, right? So the idea now is to fix this interference. So let's try to characterize what exactly has changed. And that will be the correction. Okay, so correct the past. It's literally a correction. All right. So then we are here, and okay. Oh well. Okay, I'll have to actually maybe like I don't know if you remember back, but perhaps maybe I should go to an old slide and just remind you, because this was supposed to, in the keynote, I did this all in one slide. So you remember this, right? So go back to this. We're going to use this fact. This is what I call dual representation, and I probably skipped very quickly. But if you don't care about duality, don't worry about it. Just remember that any Q sub t can be written in a factorized form where each data example is represented by a site. And the site is like a Taylor approximation, like a quadratic or a linear or something linear with sufficient statistics. Are we good with that? Okay. Is this okay? Is there any question? Happy to answer any questions. Okay. So we'll assume that you're at time t, you minimize something and you have a factorized form. So they're equivalent forms, and we'll use this to actually derive the correction. And it's from here, it's actually very, very quick. So again to say, right, this is the batch version. This is Qt plus 1, and this is the online version. And I want to write a term here that will correct this so that I will recover Qt plus 1. Okay? Now what I'm going to do is I'm going to, sorry, this projector is not good with gray, but if you could see it, you know that Q sub t, which is a batch solution at time t. Okay, this is a batch solution at time t plus 1. Now I know that Q sub t has a dual representation in terms of all the data that it has seen. Okay, so this is L hat, this is the site function for all the past data starting from 0, the prior, and this is of the example J given at time t, so at Qt. Okay, and because they're equal, this is just 1, right? Multiply, divide by something that is same. You didn't change anything. I basically just push this inside the KL and do a very simple math. Okay, what have I done here? Essentially, I've just taken the t plus 1, which is the future, to be here, and the rest of them, I've taken them here. Okay, so this first term basically comes from here. Okay, and now I'm using this previous site that I had in my old Qt. So I've changed the prior P0 to Q sub t, which is my most recent posterior, and I basically pushed their site function as a correction. Okay, so we have it. Basically, this is just, if you go in the paper, I've written the equation that you should look at is the equation number 4 in the paper. Is simply 3 lines of proof. Okay, but you can compare now. These two terms are exactly these two terms that you write in variational continual learning. I'm saying that the variational online version is actually wrong, right? Because you need to add this term. But if you add this term, you recover it exactly. Okay, and this is not a magic, right? Because I'm basically saying that all of the past is changed, right? I have to go back and fix every data example that I've seen in the past, and I have to correct them, right? And if all data has changed significantly, I'm kind of screwed. Okay, so what I'm trying to say is that in nature, there's some kind of sparsity. Sorry, what was the word you used? Parsimony. That only few things change, right? Only few things change. So there's a hope that when are you able to quickly adapt is when this sum is small. When I have to fix only a few things, it should be quick. Okay? And this is a thinking that I've been thinking about for a while, but it comes out in a very simple way now. I could write it in 3 lines, and it has taken many years to come to this simplicity. But in the next part of the talk, so how much time have I used? Oh, I've used 20 minutes, so I have a lot of time, and we can go quite, you can ask questions if you have any questions on this. Happy to, yeah.
Like in order to do the correction, right? In order to do the correction, in some sense, like I understand that this makes a lot of sense, but it doesn't respect sort of the constraints that you'd have in continual learning if you try to do it there, right? Because you still need all the data you need, because you don't know exactly which data points you need to correct. And as you move in the space, the points that you need to correct change. This is not like a constant. It's not always going to be these 5 points that are going to be problematic. They change all the time. So you basically need to go over the entire data and basically compute a bunch of things. A lot of them are going to be 0, but you still have to compute them to know if they're 0 or not. There's no way of predicting which data points need correction. So that makes the whole thing problematic, right?
Yeah, I didn't say it was easy.
Okay.
I basically laid down the difficulty of it. It clearly shows you why it's going to be difficult, when it's going to be difficult, but it also tells you when it's going to be easy. So that's kind of what I want to convince you. Okay, and the way of writing this thing also naturally kind of shows that this interference is created whenever things change, like in model merging or in influence estimation or in federated learning. And you will see that different strategies are being used to approximate these things. So it kind of helps you to understand what kind of algorithms naturally can be used that will be adaptive by design. So that's where we had it, right? So the claim is that let's take this as an objective that we want to minimize, okay? And let's think about strategies that one could use to reduce this interference that's been created, right? This actually, many things have happened here. First of all, you have a very precise way to mathematically characterize interference, which I don't know of any other definition that exists till the date. And you could correct me if you think that there is something else, but I don't know of a better way to characterize interference. So now I'm actually suggesting that this is how I'm going to call what I'm going to call interference. And I'll show you that this also, actually in the paper, I show that this also leads to a definition of information gain. Okay, so this is very closely connected to what Bayesians call information gain. And interference should be defined through information gain. And this kind of does that part, which is quite nice. And then we are saying that all sorts of adaptation tasks are trying to deal with this interference, and they're dealing with it in different ways. Okay, so we're saying that this is the objective that they are optimizing. That's the first hypothesis. And the second hypothesis is that this arises in different ways in different problems. So we'll see that if we go to those cases and think about how to minimize this, those methods will pop out as a specific case of this. And then that confirms us that we are in the right direction. And I don't have a solution to solve continual learning. So if that was an impression that I gave, I apologize. Okay, I haven't solved it. But I kind of know how to go about it, is what I'm trying to say. Okay, good. So thanks for the question. But maybe as a Bayesian, this is kind of something that I wanted to maybe first start with. Let's do the simplest example of linear regression with isotropic Gaussian posterior. And Bayesians gets shit on all the time by everybody saying you use your mean field posterior, it's pretty bad. And Bayesians also feel like, oh yeah, I use my mean field posterior, it's not good, right? So, but you don't have to feel that sorry, because there are actually other ways to think about uncertainty, So non-Bayesians are also not stupid, They are actually thinking about uncertainty in very different ways. And maybe they don't know it and they call it something else. And I want to kind of show you with this very simple example how we become a little bit more humble about this. So suppose I want to do linear regression. If I did linear regression with a full Gaussian posterior, because in linear regression, full Gaussian is the exact posterior, right? So if I wrote the online version with a full Gaussian here, then it'll be exact. But I'm actually on purpose using an isotropic Gaussian. Okay, so I know I want to find this mean in the linear regression case, which is just the least square or ridge regression map, right? So you could as well write this as theta t plus 1. But this is not correct, right? This is not an equality. So I'm going to try to correct it by adding the correction term. In this case, if you write the correction term, it comes out to be that. Okay, let's look at it for a bit. Essentially, what do you have? You have the previous, so this is like the site function that you have previously, which is a linear, which is a line. If you remember from my explanation, it was theta transpose expectation of the gradient. And in the linear model, the gradient takes a very simple form. So you can actually just write it as the prediction. Okay. So this correction term essentially becomes the difference between the prediction. Okay. And if I add this, my claim is that this is actually equal. Okay. There's a term for regularizer that I have omitted. So that's what that dot is. But on the data example, you basically do prediction matching. Okay. So if you actually were to plot this is your old linear regression line. And actually you cannot see, but God damn it. There are data examples, by the way, here. Yeah, there's a data example here. There's a data example here. You can see, but they're the old data example, okay? And I got the new data examples here. So my line changed, okay? And what this is actually telling me is that I should use this. So this is just a quadratic regularizer, like what you use in EWC, but with no Fisher. It's just identity. That's what this would be. And if you do these two things, then you should add this prediction mismatch between them all. So you don't see the old data, but there's an old data here. So you try to look at the mismatch of the prediction for that old data. There's another data point here, and you look at the prediction mismatch between the things. Okay, so these red lines are exactly the correction term. Okay, in this linear regression case, what this tells me is that if I add this prediction mismatch, I recover the line exactly. Of course, this prediction mismatch is all on the data example. So Razwan would say, oh, this is useless, right, Razwan? Yes, it is. And then Bayesians would say, how is this possible? If you're not saying it, maybe, think again, right? How is this possible? I used a mean field posterior. How can I get the exact answer with a mean field posterior? I shouldn't be able to get it. So if you actually, sorry, I missed my example. If you actually think about this, what has actually happened, and I tried to tell this last year, but maybe it was not very clear, so I rewrote this. But actually, if you rewrite this red term, if you rearrange it, you start to see the Hessian up here. Okay, so the correction term actually in the linear regression case has a very simple representation, which we call Hessian. And Hessian is just a matrix, right? It doesn't depend on T in that sense. It's a compact representation that's not like in the size of T, but it's actually in the size of the parameter. So what this correction is doing is that instead of using the covariance here, now I've added this term to account for something that I didn't use in my posterior. It's an approximate posterior. I didn't use a covariance. The correction is making up for it. So as a non-Bayesian, if you do knowledge distillation, if you do prediction matching of some sort, actually you're Bayesian, is what I'm trying to say, right? You're actually modeling uncertainty by looking into a misalignment between two models.
Can I ask a question?
Yes, it's not time yet, right now.
Just one thing is that my religious feelings are a little hurt by the covariance matrix of the posterior, in a sense that, thinking as a non-Bayesian, I want the posterior to be consistent, so to converge to the true parameter. So n will converge to the true value, but I also want the variance to shrink to zero, actually. And here you do not allow even just a sigma in front of the identity.
Oh no, you could do it.
It will work the same?
It will work exactly the same. You can even use a diagonal posterior. It works exactly the same. Just the correction will get smaller. So it's actually, maybe I could just tell the main point of the paper. The main point of the paper is to show that if your posterior is more expressive, correction is smaller. So if you use exact posterior, here the correction will be 0. You could write the math, you will get 0. Okay. So there's no, it's an equality. It's just exact, right? This is always exact. So if you use an approximate posterior with an isotropic Gaussian here, then these terms will be somehow down-weighted by that much amount, what you have already modeled, and you'll see them appear in the correction. This calculation is in the paper, so you can check it.
The calculation will not change for n, but your update in sigma will it also be independent of remembering the past yj?
So this is a very it'll all be correct. That's what I can assure you. Nothing is wrong here because it's just 3 lines of it's called playing with zeros. I've just added subtracted things. That's all I've done. So this is very, very simple actually. It's always exact. Religious feelings are hurt. Okay. Yes, please.
It's still missing the t+1 term, right? So it's not, the correction is not exact in the sense that the new data point is still not being incorporated in
the t+1 term is here, right? So this is the new term.
But the KL term, so you you are not. Are you counting for the covariance for the new data point?
It will be counted like it. So I've written only with respect to M here, but if you did the covariance here also, like optimize both the mean and the covariance, this term will contribute the x transpose for the t plus 1.
Right, but this requires that you need to have the full covariance in the new t plus 1 point, right?
So these are considerations. So like if you want to, so of course it's just not solving the problem, right? If you want to actually compute the exact covariance, you still have to compute it, right? So every problem that you solve, if you solve over mean and the covariance, it's not like you have to store it, right? Then you don't gain anything. So what this is actually showing is that if you didn't want to solve it exactly, what you could have done, right? So it's actually saying, so suppose you don't care about covariance forever, not like Pierre, who cares about it. But if you didn't care about it, you could just keep a handful of examples all the time and just keep matching your mismatch at those points. And that will model some part of the uncertainty, is what this is saying, right? Yeah. So that's kind of what actually we did. So Siddharth and I wrote this paper, 2021, that I think almost nobody understood. Even people in my group didn't understand it because it was just so weird, because something like this has never been done before. And we didn't know how to express this. And we were playing with gradients and trying to reconstruct gradients at the time. And because we wanted to reach non-Bayesian audience, so like the thinking was actually using the Bayesian arguments, but we wanted to reach the non-Bayesian arguments. So we wrote it only for the mean. So we wrote a point estimate version of this. And in that paper, we said that actually we should be optimizing the current loss. So this is not linear regression anymore. This is like all sorts of linear, nonlinear model, but let's say it's a generalized linear model like logistic regression. Then you should be adding this quadratic thing, which comes from the KL of the isotropic Gaussians, and you should do some kind of prediction mismatch. So I've written it now for a general loss, right? So it's, let's say, logistic loss or cross entropy loss. And you did something like this, that in the paper we argued that this actually reconstructs the gradient. So it can get the exact solution. And we say that actually many adaptation methods, the ones that assume some kind of linearity, they're reduced to doing this, solving this problem. And now what I'm claiming is the correction is actually a more general way to write it that just kind of works for almost everything that I have tried on, right? So in that time, I think you cannot see the numbers here, which is very weird. Perhaps if I move this. Oh, wow. Okay. It's okay. So, so yeah, it's from, well, 2 is your paper. And then there are a lot of other papers. So we went back to like the literature on SVM that are actually doing very similar things. And this gradient episodic memory that's writing the dual version. And we were arguing at the time that they're all doing some kind of prediction matching. It's kind of hard to see it in this form, but perhaps maybe I can write a more general version in the next slide. So actually, what is more interesting is that if you write this with the correction term now, and you can see the calculation in the equation 8, and I think maybe to Sarath and Razwan, this is what I wanted to tell you guys. I added this slide just for you, actually, in a sense. Maybe Siddharth will also enjoy it because this is just written very, very fresh, right? So I'm actually saying that in general, there's a separation between, there's like these kind of 3 kind of terms I've added here, right? So I have a loss function, and I'm saying something like EWC, where I modeled something that doesn't kind of change over time. And then I've added some prediction matches to account for additional uncertainty update. And it turns out that this one is accounting some kind of generalized Gauss-Newton style part of the Hessian. Okay, so if you think about uncertainty as being Hessian, then this term is adding something like from the prior, because I assumed an isotropic Gaussian. And this term is adding something like a generalized Gauss-Newton style. And actually, if you have a nonlinear model, then you have another term that deals with the Hessian of the neural network. And this term actually takes care of that. Okay, So what is this term? This term is only applied at the output of the neural network. It has nothing to do with the loss function. But you can write this term to say there's a linear, because you chose a Gaussian isotropic Gaussian approximation. So your surrogate, the side function, is linear. And it's telling you that you should somehow take care of this nonlinearity. But this term here, okay, I should have written, this term is actually the residual. Okay, I'm taking a lot of time here. So essentially what happens is that in nonlinear, so in like kind of linear cases, this term is sufficient. But if you're doing neural network, then you have to also think about some past mistakes that you've made. Okay, so you get this residual here, and the residual is the old example. If you've actually classified them wrongly, then this thing will come in through your nonlinearity and will hurt you in the future. It seems kind of weird if you look at the math. So let's think about it intuitively. It's actually a concept that's very fundamental in student-teacher learning. Okay, and Wapnick has done this work. It's beautiful, beautiful work, by the way. If you haven't read this paper, this is where it comes out. He's been thinking about how can a student learn quickly when the teacher has already learned, right? So what he actually does, he meaning they, in the authors of that paper, is that they say if you have two classes, for example, and you have a teacher, perhaps there are some cases where the teacher has actually made a mistake, because these are the examples that are on the other side of the classifier, right? So what they do is that they write a dual problem, okay, where they have slack variable for each of the example. Okay, if you remember SVM, then you will know what I'm saying. And essentially, they're boosting those slack variable by using the slack variable of the teacher. Okay, so they say that you have to only fix it at just few examples where the actually teacher has made mistakes. Okay. And what I'm claiming here, and I ran out of pages in my paper because it's already 20 pages long, so I haven't written about this, but you can see this as a primal version of that dual. Okay, so correction, if you write it as in a constraint form, each correction with using your side function is actually boosting your next problem from the side function that you've learned. And now your side function has to change. Okay, and this is exactly what appears also in the student-teacher learning. Okay, so the difficulty of the problem is actually determined by these three flavors of regularization to your problem. And some things are actually easy, like the things here and here, they are somehow easier to represent. But things here require explicit storage of certain experiences and explicit correction of those, some care. So nonlinear cases, why neural networks are hard and why online convex optimization is easy is because in online convex optimization, with linear things, this term actually doesn't appear. Okay, why conjugate Bayes is easy is because these terms sort of asymptotically, they have a very sufficient representation. They don't grow over time. But in nonlinear cases, things are hard because the mistakes can pile up. And somehow, if you're in the IID training, you're actually able to sample a mini batch randomly, and that corrects this eventually. So there are some arguments in the paper on how knowledge distillation actually does the right thing, which we're not able to do in continual learning because we don't have the luxury of storing the past examples, right? And it gives you a clue on how to approach this problem. Okay, so this explains correction term. Now I want to go into what we haven't done and what we should be aiming at in the future. Is this slide that I think I showed at Colas, but it made less sense then. but this was actually shown with this thought in mind that there's three kinds of things that appear in the correction. Okay, so think of a very similar, like a linear problem where you have actually classified something quite well, and you don't know what will happen in the future. What it actually tells is that there are three kinds of examples. Some examples that are easy, they're actually far from the decision boundary. You know them quite well, and you believe that in the future, your opinion of these examples are not going to change. Okay, so you can actually represent them in a Hessian. That is a static thing that doesn't change. But then there are some examples which are close to the decision boundary, and you expect that things are going to change. These uncertain examples, ambiguous examples will, because my line is going to move. So they're very sensitive to them. And I think I need to make sure that prediction is matched quite well when I go to the next one. Okay, so this contributes to the second term in there, in the correction. And then there are examples that are misclassified. This is on the other side of the decision boundary. Okay, and that goes with the memory. Okay, and it's not actually suggesting that you should actually choose examples in this way. It's actually saying that when you're taking care of the correction term, the difficulty of the problem grows and how you see the experiences in this fashion. Okay, so just to summarize, how to solve adaptation? This is my take on it. I think there are three kinds of things that are going wrong, right? As I said, and we could do weight regularization for examples where both feature and predictions do not change, so features are the same. We should do prediction matching to handle examples where features are more or less static. The change in the features don't actually change much, but the predictions are kind of changed. Okay. And there are examples where we have made mistakes, where we expect that there's going to be large prediction error and the features are going to change in the future. So maybe we'll start classifying them correctly, or maybe feature will change and maybe the predictions will will tell us that maybe we did the wrong thing in the past, right? So there are these three kind of things. And I think that any adaptive learning requires a balance of these three things. So now we need to think about the approximations that we make, how to balance these three different kinds of scenarios that will arise in different ways. And what it's also telling you is that the memory requirement actually increases if you go from 1 to 3, right? So this is actually the simplest thing. So EWC is the simplest thing that you should be doing it, but it's not enough. Some things are going to change and you should change them. Some things are going to change so drastically that you should actually explicitly reassess your opinion again and again, okay? So this kind of tells us that what is difficult and what is easy. Okay. So I have 15 more minutes left. I kind of go to the end, and I would encourage you to read the section 4.2 where I discuss these points. This is a little bit. So fourth section is where you get tired and you go like, this is very difficult. But well, I got tired writing it, really, trust me. It's very hard. Okay, but there actually what I show is that you can write this gap, the correction term as an information gain and how it relates to the definition of information gain that was, originally proposed by Lindley in 1957. And essentially the correction terms are added to that original definition. And that actually tells you how easy or difficult the problem is, right? And it comes down to something like this. And thanks to Nico for making this plot for me. Essentially, it's telling you that this is easy. As the new data set changes, it gets harder because the gap is larger. But it's telling me that the gap is larger because the mismatch is more. Right? It's not just that the parameter moved, but it's telling me that the predictions are changing, or gradients are changing, or the Hessians are changing. My correction is actually getting bigger and bigger. Okay? So more interference means more gain. Okay? More gain directly implies more interference. So it's actually suggesting you that you shouldn't aim for the largest interference possible. Maximizing information gain is just the wrong idea. You want the gain to be such that the learner is not overwhelmed by the novelty. Something that is learnable. And what is learnable is like what kind of things are represented well right now and what's going to change if it's similar to what I've actually learned before. Those are the things that I can handle. Okay, so this is actually trying to characterize this mathematically. Yes. So this, can you give mic to Rebecca?
Thank you. I just have a quick question about this, because here you assume distribution shift, right? In many ways, at least in your picture.
Yeah, I didn't even talk about this. Everything is shift.
Yeah.
Yes.
And how do you know then at this point? Because at some point you want to say also, you want to, because I didn't see that in the formula so far before.
Yeah.
You want to say that my past is less important than my present or something.
I didn't make any assumption about anything. Yeah.
But it looks like you would value, in your equation, it looks like you would value your past more, right? Is that not?
It's not said. It's not said in the. So the equation doesn't say it. The equation said that if the new evidence when it comes, and if you're optimizing empirical risk, meaning you're minimizing some of everything, that's the goal.
Exactly, it means everything is equally important.
Yeah, I didn't. So that's a choice of the person who is designing what to go for. And you can do whatever you want to do. And you could do it, and you can write a correction for that. Like in model merging, we add these alphas in front of all the losses. That's a choice. You could do it, you could write the correction for it, and that is fine. But I have made no assumption on, I've chosen to not make an assumption because these equations don't require me to talk about distribution shift. Because as a Bayesian, I don't believe that there is a distribution. I don't know, So I don't like distribution shift, sorry. I know you guys love it, but I don't want to talk about it because it's an assumption that I have to think about. I'm saying that it's a reverse process. If something is very new, I am saying that I want to change the way people think about this. And I'm quite serious about it. Hardliner a little bit, if you want to say. That I don't want to say that my distribution has changed. I want to say the other way. If my information gain is large, I may suspect that something in the environment has changed. That's how I want to see as a bit.
Some sort of duality.
Yes, it's looking at the backward, right? Like I'm not seeing things in the forward way. Like I didn't assume that, oh, this is my distribution. It's a religious way of thinking, Like my religion, I believe in it, and then something changes, and then you go like my beliefs has changed. But you could actually go in the future and go look at it and say, in hindsight, I believe this was a big change in my life, So I'm just saying that I'm going the other way. If the gain is big, something has changed, and maybe distribution has, if it existed, but I don't want to make an assumption about it. Thank you for asking that question, and I'm sorry if I go harsh on you. But I'm going harsh on people who use the word distribution shift, and I hope that people will stop using this word because it's not a good word unless you're in a very narrow setting where you want to analyze things. It's a good word. You can use it, but you have to be careful about this when you use this word, is what I would say. Okay, I pissed half of you now, or maybe all of you, religious Bayesians and distribution shift and continual learning, everybody. But okay, we're reaching almost at the end of the talk now. So this idea, actually just want to say a little bit about the history, This is how we started back in 2019, actually. We came to duality because it became important at that point. We were doing continual learning, and the thought at the time was that actually if something changes in the world, it has to be somewhere close to the decision boundary, right? So we said, oh, let's just store some of these points. And I used the side function at that time, actually, the simplest one that I could do. I had just kind of finished this Bayesian learning rules stuff. And so we chose the second derivative of the loss with respect to the prediction of that, the output of the neural network. This was very easy to compute. So we just took that and then kind of sampled point according to it. And it worked quite well at that time. And we were wondering what was happening, try to understand it. And it took from there to today, it took all these years to actually understand why doing this thing, that preserving something from old times, and then kind of when you get the new data, you try to now do a trade-off between the new information and the old one. Why did it work so well, right? But actually what this is kind of doing is that it's choosing memory where interference is more likely. So continual learning is the hardest problem that we are facing, right? I think we have simpler problems to solve. And they can give us the clue on how to choose this memory. But I think this is the problem. What do we want to preserve? What do we want to change? And how do we represent the old knowledge compactly in certain places? That will depend on the assumptions that we make about the world. And then you can talk about distribution shift. And you can say, oh, I expect the distribution shift will happen after these many tasks or after these many time steps. And they can help you to choose the memory, and you can test them if they were right or wrong. How much this, right? So this is kind of what I didn't do in the talk. And
very sorry, like you were provocative in your claims about distribution shift, so I take the liberty.
No, don't apologize.
It seems to me that what makes it work here is that, okay, you would have had to store actually all the X's, and you decided, okay, that you're going to make an approximation by trying to remember like some kind of relevant experience from the past, etc. And the way you chose it was because, in a sense, you expected a certain form of shift.
Yeah, I made this up. Exactly. No, but
it is believing in distribution shifts. That is not too bad. You said that it's not going on the left side.
Sorry. This is a toy example. So in the paper there's MNIST and CFAR 10. If that is, I mean, that was like 5 years ago. So it does work to some extent, but it's not a solution, right? Because yeah, you're right. I agree with you. Thank you. Okay, so we have had some success in this, but not nearly. I'm not happy with this. In ImageNet, we can do something, get close to this, but I don't want to talk too much about this thing. What actually excited me was in LLM, and this is the work that Nico was mentioning day before yesterday, is that there for model merging, if you write the correction term with an isotropic Gaussian, it simply is the mismatch between the gradient. Okay, I have not shown this to you today, but in model merging, the correction term becomes gradient mismatch. And if you measure, so this x-axis is the gradient mismatch, and the y-axis is the test error. So what this kind of shows that if you did a simple version, and then you try to reduce the gradient mismatch to make a version that's better, by theory, this is decreased, right? So the test error is also decreased. So this is quite, it shows that the theory also kind of works in practice. But we have actually, this is what we've been doing. So we've been kind of working with federated learning, model merging for this reason, because there we didn't have to, we had access to all the data. So it was a simpler case where we didn't have to work with memories, and that helped us to understand what kind of correction is being optimized in these cases. So like if you want to do model merging and federated learning, essentially your knowledge is stored in Q1 and Q2. So you'll form some kind of, an ensemble, or like some kind of Bayesian arithmetic that we talked about on 2 days ago. And you will now want to add knowledge on top of it, right? So when you merge Q1 and Q2 together, they interfere with each other, and then you get the interference on their losses. And this becomes gradient mismatch actually in the paper that Nico has written. So this is model merging by gradient matching. That's the paper that I showed in the previous slide. But this also happens in federated learning. Okay, and essentially what we show is that if you choose a different Q form, right, then we get different strategies. And if you use a better Q form, then the correction is smaller because it represents more, and the correction that you need to do is easier. So there are two ways to represent things. You can store a really big Hessian, or you could store a diagonal Hessian and store a lot of points. They're kind of like same similar ways of doing approaching the correction. Okay. So I really think that compact memory is the thing, and I think in the afternoon Thomas and Siddharth will talk about this. So how do we design algorithms that minimize corrections? And it turns out the ADMM is that algorithm. So in the paper, actually, they don't write it like that because correction paper was not yet out there. But if you read the correction paper, I write why the ADMM style methods can actually drive correction to 0. Okay, but in this case, they have access to all the local data, but the data is not shared. So there's some kind of restriction, but still you can drive correction to 0. So it's very interesting that that can be done, right? So this gives us some clues on how we can derive continual learning methods that do the same. Ultimately, so this is actually what Thomas will talk about, but this is basically IVON modified for federated learning, right? So the future that I see is that we'll have some algorithm like IVON or maybe even ADAM, and then we will modify it to aim for the correction. Okay, so there will be these kind of red parts that are added somehow to improve the IVON algorithm, and Thomas will talk about this in the end. Okay, so with that, I close the talk to tell you, right? So I said two things: Bayesian learning rule and posterior correction, and these are the two things that we have done in past 10 years. What I think, what I haven't answered, and I would encourage you to read the discussion section of the paper, which I absolutely always love to write, because this is kind of my view of the future of what has been done and what still needs to be done, is that I haven't answered this question, like what should the algorithm remember? This is not answered, right? It's kind of saying that you should remember something to minimize the correction, but we don't know what exactly. And what kind of new experience it should seek in the future. So it's this kind of game between past and the future, right? What should I remember from the past? What should I go for in the future? This question is not answered, but the stage is kind of set. The stage is set in the sense that you should think about your memories. They should be chosen so that we may, minimize some corrections that may arise in the future. It's like thinking about curriculum for our baby robots, right?
You can never predict like what kind of corrections are needed.
You can, like you could train the GPT and then you can think about its curriculum that next time you would not have to retrain it from scratch. It's called mid-training these days, I think. Mid-training or continual fine-tuning. I think that's what they're trying to do. Right? Does it make sense? I don't want to retrain again and again. So you could actually reflect back and you could go and like adjust and make some, say that these things were important. These checkpoints were important, right? Let's restart from there. Given a new future, let's use these checkpoints, not the other ones, right? How do you make those decisions? The correction is actually helping you do that. So if people use this framework to do that, that'll be amazing, right? Maybe a DeepMind. Yeah. If you're done with Gemini, maybe this is what you should be working on. Okay, so then it's the same thing, like new experiences should be chosen to enable easy enough corrections. So don't choose corrections that are too hard. Yeah, it doesn't solve the problem, but it's kind of setting the stage on how to think about this. And I really think that, like, I think what you were saying, right? The future is unknown, right? And you may say, oh, well, and I cannot store everything in the past. But, we all do this all the time. We don't remember everything that we've learned in school, right? We don't even remember anything that I said today, right? But I know that you'll read the paper and you'll remember back, right? You as an agent, you're free, you have the freedom to explore the world, to fix the past and choose the future, right? And that's, I think, how things can happen. I was in NUS and they were writing, celebrating the past and shaping the future. But, as somebody who doesn't like colonization, I think I don't believe in celebrating the past. And I think my research has actually contributed in that sense that I'm saying fix the past, please, and choose a better future. Okay? All right. Okay, so I'm done. Yeah. Yes?
Yeah, how important are the memories? Or could you go without memories?
Yeah, they're extremely important is what actually all of this showed. So I don't know actually how to, so we're working on memories. So
I mean, if you can't store with examples.
Yeah, if you can't store, you are in a trouble. So if you're using a model that's highly nonlinear, right, it's actually telling you that you will have to put effort in like thinking about these mistakes that you've made. So like in the bad setting, you get away from it. Right? I actually think that for continual learning, the future is not that we start from nothing and then learn. The future is more like I have actually trained models and I should reuse those models. And so those are the memories that I I think storing memories in terms of models is the most sensible thing to do.
You don't say that you necessarily need samples as memory.
No, I think you need compact memories. So what I have convinced myself by looking at this is that if you look at the split and the samples, you will see that there are certain samples. If you work in the nonlinear case, you can never control their complexity, right? So in this sense, they're, as you said, right? In the worst case, they may be growing linearly, and that's really bad, right? If you're in an easy case, maybe they grow log linearly, right? So perhaps if you store these POS models, there is a hope. And because the batch methods can do it, I think we can do it, you know. If you can learn something in a batch fashion, I think that's a sign. Like you have your language model, you can learn by one pass through your data, right? I think there's a sign that just with the model parameter, you can actually represent a lot of things. So I'm not too worried if I have to retrain GPT's level model. I think this is possible.
I got the mic. So can I go next? So I was lucky. You go first. So you also have a mic.
No, I was just keeping the mic in.
He's just a chair.
Okay. So thanks. I have a comment that is not my actual question, if you don't mind, just to what you said. Is when you want to store models, isn't that kind of a bigger problem in comparison to storing the data? If these models are highly overparameterized, so we have many more parameters actually in neural networks than potential data points. So kind of it's worse than storing models.
Yeah, I don't have an answer to that. I actually think that we need to store part of the representation somehow, right? Yeah. So I think Andre and I were talking about this. In the future that I imagine and I would want is a federation of models that have interfaces at different level that gives me access to their knowledge at a different granularity. Like the last level of this is the data examples, right? But I would want, like, I think with people, we do this kind of thing, you know, we have intense conversation or we have usual conversation, we have meeting like this where we share knowledge, right? So I think models will have these kind of modalities, different ways to transfer knowledge. I don't know how exactly it goes, but I would love for it to have like, you know, different levels are more difficult so that they're more costly, so you pay more, and that kind of makes the marketplace a sustainable market where people own their model and data and share their knowledge in that fashion. Yeah, so let's see. Yeah.
Just as the actual question that I would have also in this context when it comes to this is, I'm wondering still a bit about how do you weigh the past that you want to collect in comparison to the future or to the present that you have.
Yeah.
And what you're assuming with fine-tuning models is kind of you're saying like my future or my present is much more important in comparison to my past because now I adapt my model in such a way that it is good on my new data set and just use the knowledge to improve my optimization. This is what kind of fine-tuning is doing, right? So it make but I don't care too much about the past in a sense. And
well, I don't know, right?
Right, in connection terms, they actually state that it's not okay to just use the model that I have at time t and just do an approximation there. But you're actually saying that no, I need to do the correction for the full past kind of, but also kind of assuming that my world hasn't changed since then.
Yeah, I mean, you just think of it in the other way, right? If you think like somebody Bayesian would come in and they would say, I need my exact posterior to really know all kind of decisions that could go wrong. Like think of like people who care about certification. They'll say, I need to know with guarantee that something will not fail up to this precision, right? I think if you think in that terms, the correction term is giving you that handle over the posterior, right?
Assumes inherently IAD. They assume that, right?
Let's fight about it somewhere else. What is what I would have said, but sorry, I think maybe we have misunderstanding about what Bayes is. Yeah.
A question is more, actually two questions. The first one is more like a thought. So from your equations, this last term in the correction where you actually have the error of the function with respect to its linearized version. Yes, exactly. So this one. This seems to suggest that models that actually are well approximated by the linearized counterparts, like super over-parameterized models, seem to work a bit this way, could actually need less correction. Right? So
the model that make less mistakes, the model that generalize better, need less correction. That's what it's saying. Yeah.
Right, but also if you make a mistake, if your model is kind of biased to work in a linearized fashion, then
I don't know what that means.
Like for instance, I'm thinking MTK-like models where in the very over-parameterized regime, you can actually linearize around some point, and your function evolves in the space of the gradient of the model as a linear function. So this means that you can actually write your model in a like you wrote the error with respect to the linearization there. I think this is something that actually has been shown that in some cases, so for instance, over-parameterization, or with some choices actually of the optimization of your architecture, you can reduce. So you can reduce that error with choices of architecture or optimization. That's right.
Yeah, I mean, I didn't see it this way. I saw it exactly the opposite. I thought if you're in a nonlinear case, you're gonna have a problem with this.
Yeah, so that's why it's interesting.
I don't believe in NTK also. So yeah, I think function space priors are not gonna work because of this reason. These are all opinions that I've come up with. So I think we work with very nonlinear model, then these terms do exist and they are significant. So if we make mistakes, we have a huge cost to pay.
Yeah,
right?
But I think it's interesting because it seems to suggest that, like for instance, feature learning. So when you enter the feature learning regime, you have more nonlinearity, right? So this error is higher, and it seems to suggest that for continual learning, actually feature learning is detrimental, right? So either you don't make a mistake or you reduce your.
Yeah, it's very hard. It's just telling you things are hard.
Yeah. And then second question.
Should we be doing this or? Yeah.
For the information gain part, where you were saying if we can choose the future, maybe we can choose the future with lower information gain. But I remember from like maybe intrinsic motivation literature, it goes a bit back.
I know.
That actually the suggestion is to look at, for in the input space to look at points that have higher.
And I am disagreeing with it. Very strongly disagreeing with that way of thinking. Like in experiment design, people say, let's go to the highest place. That's actually not correct.
But why would it be not correct? From your equations, it seems just that you would anticipate the mistakes before, right?
There's more to the story than just simply saying, let's maximize the information gain. You have to put some constraints, and you cannot be just like, let's do epsilon. Anyway, this is kind of more, I don't have much, I just have opinions. I don't have actual research, so I just become a bitter, angry person at this, Maybe let's talk about it later. Also, we have to take a photo, so yeah.
I was just going to ask one question. I'm trying to think about this from the perspective of living agents, right? So you have a rat, you teach it A, right? Then you force it to unlearn A.
Yeah.
And then you teach it A again, and it's suddenly faster at learning A the second time than the first time.
Yeah.
And so I was wondering, could you apply what, and I've been trying to think of how to apply it myself, but it'd be easier for me if you told me how that applies in this situation.
Oh, I actually don't know. Wow, I would like to think about it. I don't know. That's incredible.
And related, no, I promised one question, so I'll stop.
Okay.
I just had one.
Just press it one more time and then.
Sorry, I muted it.
Yeah.
Okay. So I just had one thought. Maybe it doesn't make sense, but I like all of this quite a bit. So I think this is cool stuff. But it's all focusing on interference, and to me that feels like it's missing something. Because like the goal of learning is not just to avoid interference. If I would have a hash table, like then I would not need to correct anything about the past. but somehow that doesn't work. Well, the predictions will stay always the same. So it feels like there's nothing about, like, it doesn't capture sort of how the past is helping you learn more efficiently in the future. Like, it doesn't, that interaction is not.
I think it's there, maybe just hidden so you don't see it. So that one I can actually, I have, yeah, because it's when you assume the hash table, you're actually assuming that you have perfect code, like somehow things are, so you store you store things without any loss, right? But that's actually done in the posterior form. So then you may not have corrections in that case if you think that that's correct, but you made an assumption there. Okay, we could talk about it later, yeah.
Thanks. Yeah, I'll talk about our ICLEAR paper, connecting federated ADMM to Bayes, and then hand over to Thomas for, like, I guess the second talk, which is a continuation, I guess, of this work in a new paper, which is like much tighter linking or like recovering and extending ADMM using Bayesian duality exactly. So this is like, in this first half hour, you'll get some high-level insights as we were sort of exploring federated ADMM and Bayes and finding out a lot of the links that exist. And then that's in this paper, and then get into the more nitty-gritty, like, mathematical details as well later. So I'll start with federated learning, like just a brief introduction / recap of what that is. So data is often distributed heterogeneously across many devices or locations. So for example, you can have many clients. These can be different mobile phones with all, like, personal data on them. It could be large institutional databases like medical records in hospitals. So each client would be a different hospital with their own set of patients' data. And, like, crucially in federated learning, we're sort of focusing on things like security and privacy of the data. The data must never leave the client where it's stored. You don't want the hospital sending off patient data to other hospitals or to other people. And the aim in federated learning is to still train a global model as if you had all of that data available in one place, even though you actually don't. So you have this global server, it's communicating back and forth with all the local clients, it's communicating model updates or something, not the data itself. And it's trying to learn a global model that performs well as if you had all of the data. Some challenges in federated learning that arise, for example, so the different clients have heterogeneous data splits. You can have very different kind of patient data in client 1 compared to client 2, which can make it very difficult to communicate, like, the right information, or things can sort of be in conflict with each other. Clients can just drop out, so there can be a lot of heterogeneity in, like, the system level. Clients can drop out, they can become disconnected, there can be a noisy communication channel. With the case of mobile phones, you might just lose internet sometime, you might not be able to send all the data you want, or the model update that you want. We're not going to look at, like, the latter kind here, sort of focusing on the heterogeneous data split part, which is already difficult enough. And the key requirement or aim or objective in federated learning is to minimize the communication cost. So you want to reach a good model performance on your global server as quickly as possible, with as few communications as possible between the global server and the local client. Like, communication is expensive, bandwidth is limited, so on. And for this paper, for this first half hour, I'm going to talk about connecting federated ADMM to Bayes. So really what we do is look at and find new connections between, firstly, ADMM or federated ADMM methods, and I will get into what those are and motivate them, and find connections between those and variational Bayes methods towards federated learning. So then I will also motivate those, and then see some surprising, maybe, similarities between the two. For example, dual variables in ADMM emerge from the site parameters in variational Bayes. And I'll point these out once we get to it later in the talk. Okay, so let's formalize mathematically a bit more of what's going on. So I'm going to say there are capital K clients. Each of them has dataset D1, W1 to dk. And we want to learn these global parameters W sub G. So I'm calling the model parameters W in this talk. I think most other talks it's theta, here it's just W. So it's W sub G, and we want to learn these efficiently in terms of communication cost, and securely, meaning that the data D1 to dk is not allowed to leave the clients. The ideal WG star that we would learn eventually is just as if we had all the data in one place. We don't, but it's as if we did. So this is like an argument of the sum of all of that data, and I'm just calling it L sub k for the loss on data dk. And there is potentially, there's allowed to be a regularizer. In fact, in federated learning methods, historically, people don't use a regularizer, this eta or whatever. Regularization strength would be 0. But obviously, we will have a regularizer. Bayesian methods usually have some kind of prior, and you'll see how that all fits in. So there are 4 steps, I think, in terms of how the majority of federated learning algorithms proceed. In the first step, the global server sends the current WG, could be bad, it could be good, whatever the current WG is, to the clients. In the second step, each client uses WG and its data dk to learn some parameters at the client locally. So it does some computation, does some like update steps, some mini batching, some gradient updates to learn what I call WK. In the third step, it sends the WK, or each client sends their own WK back to the global server. So W1 through WK, W capital K. And then at the global server, we combine all of these W1 through capital K using some kind of function to update our WG. And then we repeat. So then this new WG is sent out to all of the local clients. Each client updates, sends back, and repeat. So I'm going to go straight into like existing methods to motivate ADMM or federated ADMM methods. See why they're a good idea, see what sort of useful things they do in federated learning. Start very simple. So federated averaging was, I think, actually the first federated learning method, and like the paper that probably, I think, coined the term federated learning. And then fedprox is just a very slight improvement to that. So federated averaging is without the red part, it's just the argument. So at each local client K, this was, I think, step 2 earlier, it takes the WG and it does some update, right? So federated averaging, all it does is it just takes a few number of update steps locally on the loss LK. It doesn't even use WG. Actually, it initializes at WG, then just takes a few gradient steps. And that's what the new WK is. That's why I call it approximately augmenting this loss, because it doesn't actually augment the loss, it just takes a few update steps in that direction. And then at the global server, you have to combine all the WK somehow, it just sums them. These NK over N is just a detail about making sure that if you have more or fewer data points in one or another, that things work out, but essentially we're just summing them, summing all the WKs. Fedprox then adds this red term in, this L2 towards WG into that loss. So it just locally, each client is locally pushed or is encouraged to stay towards WG where it was initialized. And this is to make sure that each client doesn't go off and do its own thing. It's called client drift in federated learning, where each client can then go off and like optimize for too long on their own data. So to avoid too much of a client drift, they added this term to just push it, to help it remain within some ball or close to WG. But it's missing, I think, what would be an ideal or something that we would want from these algorithms, which is that at the stationary point of the algorithm, we would target the correct things, which is that all the WKs should become the same WG. Like we don't want all these clients going off in different directions always. At the end of the algorithm training, that should all be the same. And also we would want that WG obviously to be WG star, the ideal thing, as if we had all the data in one place. And with federated averaging and fedprox, we definitely don't have this first one because WK is always approximately augmenting something that has the local data. And the second one you can prove in certain situations if you're like very careful and restrictive. but we can do better. So that's where federated ADMM will come in. It's also, so both of these algorithms are also very sensitive to the number of local iterations, as you might expect. If you take very many local iterations at the local client, then you have this huge client drift, which makes things very difficult. And then when you just sum them together in the global, these are all very different things with client drift, and it just doesn't really work. So you need to be very careful with how many local iterations you allow. So that motivates, we'll go straight into federated ADMM. I mean, there are other methods like along the way that we could talk about, but go straight into the one we care about. And there we just add 3 things. I should have highlighted the second line as well. So we've added this VK old, VK transpose W thing here. We've added an entire new line. This one, something to do with V's. And we're not just summing WKs, we've added the V in here as well. Those are like the high level changes that have happened. And these have been like motivated through many things, ADMM being one of them. And that's why I call it federated ADMM methods, but also through proximal dual relationships or through dynamically matching parameters. Doesn't really matter. All of the algorithms end up looking like this. And what's happening is that we've introduced this VK, which, as also I think Thomas will show mathematically, can be viewed as a dual of something. These are these dual parameters or dual vectors. And what they're doing is they're constraining or helping ensure that the WKs, the local client WKs, are equal to the global WG, at least at convergence. So this is actually comes out from this constraint. And that's where the VK transpose W comes in the first line as well. That's like the Lagrangian, but just deleted the WG out of it because it's an argument over W. Anyway, that's details. So all of this is about adding this constraint in. So yeah, as I said, we've changed the local client objective now so that at a stationary point, WK is equal to WG. And also that this is all equal to WG star, which is the thing that we want, the optimal, the global objective we're aiming for. So having introduced federated ADMM, now we're going to go into Bayesian methods and see how that's similar to federated ADMM. And then the next talk with Thomas is going to recover and extend this algorithm, federated ADMM, from Bayesian duality. But right now, we're just going to focus on existing Bayesian methods, how we can massage them or change them to look similar to this, and how we can take advantage of that. So I'm going to switch over to Bayesian federated learning. So for the next like 1 and a bit slides, I'm going to just ask you to cache all that information about federated ADMM and then bring that back later. So in Bayesian federated learning, we're learning an approximate posterior. We're not just learning like WG, we're learning Q sub G of W. And this is it's the prior times a bunch of likelihoods. And we're going to use these T sub Ks, these sites, we can call them sites, to approximate each client's data likelihoods. There's a K of them, 1 for each client. The Bayesian, so the aim is to learn an approximate posterior distribution over all the data. And variational methods have, for example, Gaussian approximations for these site parameters TKs and a Gaussian prior P of W. So then the approximate posterior is also QG is also Gaussian, and that is what we are learning. And we want to learn this iteratively through many communications. So here's one algorithm. I just want to point out the high level details. There's a lot of notation here. And I want to point out how this is now similar to federated ADMM from what we saw earlier. So this algorithm is partition variational inference, PVI. It's a variational based approach to federated learning. It has 3 lines to it, just like federated ADMM did. The first one is an argmin over Q, similar to federated ADMM argmin over W. The second line has some kind of addition, subtraction stuff going on. It's actually very similar to the VK update that we had earlier in federated ADMM, at least superficially, like as we look at it. And the third line is some kind of summation over these t hats. And what's like very interesting is, so like federated ADMM, firstly, there are two equations locally. Secondly, we're storing these or using these t hats, so actually log t hat k's locally. And these actually map very nicely over to the duals VKs from the federated ADMM algorithms. And thirdly, we have the same kind of properties in PVI as we did with federated ADMM, which is that a stationary point of this algorithm is the full batch solution that we're aiming for, this WG star, the QG star, the ideal thing that we can get. And also that the QKs are equal to QG at a stationary point. Just like earlier, we had the WK was equal to WG after we added these VK constraints in ADMM.
Question.
Yeah.
Does that depend on assuming that your TK? Sorry, does that depend on you assuming that TK is Gaussian?
Yes. So
the 1 and 2 and 3 are not true. Sorry. Like what you're saying that like local approaches global at a stationary point may not be true unless your approximate likelihood is Gaussian.
As long as everything is the same exponential family, I think.
Everything like prior likelihood, approximate likelihood, Q.
Yeah. Otherwise the equations won't come out so neatly.
Okay. Yeah.
Well, I think the equations are probably still correct. It would just be more difficult to do. For now, we can just consider everything being Gaussian. That's all we do. That's all PVI paper did. But I mean, things do hold for non-Gaussian exponential families as well. Cool. So what we're going to do now is simplify this algorithm with all the logs in it and t-hats and all this stuff. And we're going to simplify it in a way that it looks much more similar to the federated ADMM algorithm we had before. And we're going to look at what that might imply. So I've repeated, that's the same equations from PVI. And what we're going to do is make a Laplace kind of approximation. So that involves two steps. First, we're going to choose isotropic Gaussian distributions. So there's a lot of notation here, but you'll see each one of these is a Gaussian with some mean, which is the WG for QG, and like an isotropic covariance, which is like just the identity matrix divided by delta. So we have some prior precision delta, some precision delta. And then again with QK, just the mean is WK, and with the prior, the mean is 0. And then we're going to make a delta approximation on these expectations that we have. What that means, for example, is that this first term over here, the expectation with respect to Q that we're learning of the loss is just the loss at the mean of Q, at the loss at WK. These two things you can always do to a variational method to get a Laplace kind of thing. So we're just going to apply that to this method, to PVI. And this is what happens to the algorithm. It's just sort of simplified some of the notation. Instead of calling things t-hats, I've said that the mean of t-hat is v to make it look more similar to what we had before. So now we have these appearing everywhere. And I've highlighted in red the only differences to federated ADMM that we saw before. So there's like 3, I guess, differences. The first is that instead of having some parameter, so earlier, I mean, I could maybe just take me out my word, we had some parameter there, alpha or something, that was the weighting on these terms for this W minus WG squared term. So now that weighting has turned into a delta over NK. This delta was our precision of our isotropic Gaussian, so it has a meaning now. And also it's being divided by or weighted by 1 over NK, NK being the number of data points. So what we're saying is that this should be weighted and also is related to how like certain or uncertain we are, at least in a prior kind of way. The second difference is in the second line. Again, we have the same delta over nk, and we have this rho term. Also, I lost my mouse again. Rho is another constant, another like scalar between 0 and 1 that we've added. It's like some people in EP land would call this a damping factor. It kind of ensures that things progress nicely. Earlier we had whatever alpha from before as well. And the third difference is in the update for global server, where now we are summing the duals, v tilde case or v case, and they're weighted by this delta of nk thing. Whereas earlier we weren't just summing the duals, we were summing the wk plus some dual thing. So we've lost these wks from the global server update, but we've kept the dual part. That's the difference. And I think, like, I guess this was nice for us to see, to be like, okay, we've taken a Bayesian algorithm and we have made some approximations and we have reached something that is like very closely corresponds to completely different kind of algorithms, ADMM, federated ADMM style of algorithm. So I think this is like the first or key result of this work. When you code this up, then you see that FedLab actually performs at least as well, if not better, than federated ADMM or FedDin, which is a variant of federated ADMM that people sort of changed a few things around and found just worked a lot better. So one of the things that they changed in FedDin compared to federated ADMM is this weighting 1 over nk that we find automatically pops out of our equations. It doesn't in federated ADMM. People found empirically that it helped a lot in their results, and that's how they ended up with FedDin. We perform at least as well as that.
Okay, can I ask a question?
Yeah.
So the global server update it's a major difference compared to the ADMM.
Mm-hmm.
So it performs at least as well as federated ADMM, but is it solving the same optimization problem or not?
It is targeting the same loss. It's solving the same problem.
Converge to the solution
Yes.
of the original Fed ADMM problem with these global server updates?
There's one difference, good point, which is the regularization delta. So FedLab here, this algorithm, is targeting the loss with a regularization, an L2 regularization. Whereas I think, as I wrote federated ADMM earlier, it is not. So like you have to like take the limit of deltas to 0 or something to get, or I don't think that works here, but there's a slight difference. I am fairly certain, although I would have to write it out to be sure, that when you rewrite federated ADMM with a loss, with a regularization term, the exact same difference will remain in the global update. So that doesn't affect the global update. I think Thomas did this at one point. It's true, right? Yeah. Yeah. So yeah, as of now, yes, there is a difference. I'm not really commenting on what that's doing, other than empirically that doesn't seem to have harmed anything. In the next talk, we'll like sort of pick up on these differences a bit more and like actually come up with a Bayesian version of ADMM. So as I said, first key insight, there are these similarities, very interesting. Second key thing was, now can we use this to improve ADMM methods? And classic Bayesian way, what can we do? We can improve the quality of our approximate posterior. So we can, instead of using isotropic Gaussians, we can do something better. So I will just talk about one. So there were two algorithms that we had. I'll talk about one in detail, which is FedLab Cove. We use full covariance or diagonal covariance Gaussians instead of isotropic Gaussians. It's pretty formulaic. We just use full covariance. I'm not going to write down all the details of how we get there because I don't want to like bore people with even more, like twice the number of equations as the last slide, but you just basically use full covariance Gaussians and make a second order delta approximation instead of using isotropic Gaussians and a first order delta approximation. And you get something that looks a little bit messy, but it's actually quite simple. In red are all the new things, but the key part is basically there's an additional update at the top, in the top right. Sorry, the mouse is very laggy. There's an additional update up here for covariances. So essentially we're learning covariances as well as means now. Sorry, I should have said that first, right? Because we're learning these diagonal or full covariance Gaussians, which means that we have basically double the number of steps because we are learning both means and covariances. So we have to update both of them. So that's why there's so much more equations here. So one of them you can see in the top right is the additional update for covariances, which uses the approximate Hessian HK, unsurprisingly, because the Hessian is bound to turn up when you're using second order information. And then all these red things here, like this capital VK is then like the dual variable equivalent for the precision or the covariance part of things. Little v is almost exactly the same as before. We just added these S's. Now these S's are covariances that we're learning along the way. So what we're saying is that all these parameters like WK is weighted using the, in this case, precision, I think. SK, covariance, precision, SK, yeah. So instead of just setting all these S's to the identity matrix, these are now things that we update over time, like update in the method and use to weigh all of our parameters.
Question. Why is it more natural to consider?
Can you use the microphone?
Okay, so why is it just mathematically easier to make kind of like your approximating family richer, like Q full covariance, rather than say, like, you could change the variational approximation problem in many ways, right? So you could change the divergence, you could do lots of other things. Like, why is this the natural thing to do?
So I guess from like a variational perspective, if you're targeting the elbow, which is the lower bound, you could target a different thing.
Yeah. I mean,
but that's going to change the equations in like a much bigger way. That's going to be a lot harder to like reason about easily.
I guess maybe I'm missing a key piece, which is the goal. The goal is to derive something like that's similar to these non-Bayesian traditional algorithms, right? And that's the idea. And then so now when you like, if you change too much the setup, like the variational objective, then you might get updates, but they don't look like ADMM. Is that what you're saying?
Yeah, so I'm viewing this like we started at something that looked like ADMM, and then we wanted to add more, like we wanted to improve that algorithm, right? One way to improve that algorithm is by adding second order information.
That would be one way, right?
Right, so if we choose that way to do it, then it's very easy to do, given this view.
Right.
So that's essentially what we're doing.
Right, but you're saying there's nothing special about this, right? So like as in like we could choose some other way to improve the approximation, or
we could do. Now, if we were to change the divergence, for example, I don't know what would happen. Like I'm not sure these equations would hold. Yeah, I suspect it wouldn't work.
It just won't work.
Okay.
I mean, maybe you can. Android knows a better way to do it. But if you change the KL to something else, all of this falls apart.
I'll ask details later.
Yes. I think you were not there in the 2 days ago.
I was sorry. Probably asking things people already know.
Yeah, we talked about this. You change Shannon entropy to any other entropy, the factorization is not there, and then you don't simply get sums in the last equation.
Oh, that's from your, okay.
Cool. I mean, I'm actually almost at the end. So results, FedLab Cove, happily, thankfully, significantly improves upon FedLab. So adding the second order information, which it helps improve performance. I think Thomas will go into a bit more of the intuition also as to why that might be a good thing. But essentially, I'll give you a one-sentence intuition, which is data is very heterogeneous, split everywhere. So maybe we want to be communicating like uncertainty information through second-order information to help away things or help away information in a good way. But I'll leave that for the next talk. Yeah.
So when you say it improves performance, is it like how do you measure performance? Is it just accuracy or whatever less loss, or is it like the convergence speed? So how many iterations you have to do?
Yeah, so I'm not actually providing the tables of results here. The way that we did it is after a certain number of communication rounds, how good an accuracy do you get? And also how close can you, like, how quickly do you get to the, like, a good, like, close to the best possible? Which both of these are ways that people in federated learning test these algorithms.
Right, so without the covariance information, you could still get to the best possible, but maybe with more iterations or more communication rounds, as you said.
Yeah, everything theoretically should reach the best possible, as we said. All the federated ADMM, FedLab, everything, if you trained it for long enough. So better means that it's quicker. Yeah. I don't know why it stopped sharing, but
saying it's your time.
It is saying it's my time. I mean, I just had a summary slide, so we can actually stop there.
You haven't you will have to show results?
No, I'm leaving the results to Thomas.
Okay.
Cool. Yeah.
Okay. Yeah, I will continue seamlessly from Siddharth's talk, and we already saw that we were able to recover something ADMM-like, but not exactly ADMM. And here we will see how we can exactly recover ADMM and make connections to methods from optimization. And the derivation in Siddharth's talk was from a Bayesian viewpoint. Here we take more an optimization viewpoint based on duality. And the paper is out. So it's joint work with Siddharth, Finale, and Emti. And you can find it on arXiv. And we also have we made the code available on GitHub. In the previous talk, we also wondered, so why, if we make now our posterior approximations more accurate, why should that improve our performance in distributed or federated learning? And here I give a very simple example. I changed the notation from W to theta. So the W in Siddharth's talk is now the theta in my talk. And the question is, what information should we actually exchange between the clients and the server to arrive at a good solution? And if we look at the most simple problem, which is computing the mean, there's a 1 over n missing, I guess, but for the argmin, it doesn't matter. So computing the mean of a bunch of numbers, xij, and each client has a few numbers. We can already reason about this question, what information should be exchanged. So let's say client 1 has the numbers 1, 2, 3, and it computes its mean, which is 2. Client 2 has the numbers 4, 6, 5, 5, 10. If you do the math and compute the mean, hopefully it's 6 if I didn't do a mistake. And then the question is, what should the clients communicate with the server to arrive at the correct solution? And the federated averaging we saw, they would simply communicate their solution, which is the mean. So they would communicate, client 1 would communicate 2, client 2 would communicate 6, and then federated averaging, we would average it, and we would end up at 4. But if we do the math and sum everything up, we actually know that the answer is 4.5, not 4. So it's 6 plus 30 is 36, and then you divide this by 1, 2, 3, 4, 5, 6, 7, 8, 36 by 8, you can do the math. So the question is, what should the clients communicate? Maybe you have an idea. Instead of sending only the mean, what's a very economical thing they can send so they can arrive at the correct answer in a single step?
The size of the sequence.
Sorry?
The size of the sequence.
Yes, very good. So, yeah, very smart audience. So we should send the size of the sequence, and as Pierre said, that also is the posterior uncertainty, the precision, so the inverse variance. So if you communicate those, then we can converge in a step. So it's very natural for distributed learning actually to be Bayesian, because then we can converge much faster. And this not only holds on this very simple example, but okay, it's still a simple example. This is a, but slightly less simple. This is a logistic regression problem, and where the data is split, and client 2 is very simple. We see it down here. There's no challenge on, but then on client 1, actually there's an outlier, and this outlier forces the client 1 to go to a really wrong solution. And it takes a lot of time to correct with, so this is learning with federated ADMM, like after 1 communication round, I'm here, 3, 5, so it takes 5 communication rounds to correct the mistake made by this outlier. But if you have a Bayesian setup, you're actually keeping this uncertainty, and you're already skeptical about this outlier from the beginning, and you're also saying, I really want to be uncertain here, so these are these vertical dashed lines is your uncertainty about the solution. And then this allows you in a single communication round to actually adapt to the correct solution. So you get much faster, similar to the previous example. We can just learn much faster in a distributed setting if we are Bayesian than if we are using the optimization method. So this is also a reason why we expect better posterior approximations in federated learning to give faster convergence and better results. And yeah, this is the overall, this is what the server sees, and we can see the Bayesian method converges in a single step to the correct solution and maintains this uncertainty, whereas the federated ADMM on the server, it's getting biased because of the outlier, and it takes 5 communication rounds to correct this mistake. However, existing federated learning methods don't use this uncertainty. So we've seen it already in the previous talk. We've seen the federated averaging. It's just doing the naive thing, federated procs and federated ADMM. They are just estimating the parameter. So we've seen this already in the previous slides. Here I rewritten the federated ADMM in a slightly different way, so it looks different than on Siddharth's slides, but it's equivalent here. It's for an L2 regularizer. So the last update is actually a closed form solution for an update like this, where R of theta is the L2 regularizer. So these are the existing federated learning methods, and now we will see how we can get the ADMM method from a Bayesian viewpoint. So to arrive at this, first we derive ADMM, and we derive ADMM using a dual viewpoint. And the way we do this is we have our server variable, which is theta bar. We have our client variables theta 1 to theta k. And we have dual variables Lagrange multipliers v1 to vk. Each client has their own loss function. We have Lagrange multipliers which say, okay, each client should be the same as the server. So if you would maximize that Lagrangian with respect to vk, that would give us plus infinity if they don't match and 0 if they match for this term. So this term basically forces all the clients to eventually converge to the same solution as the server, and L0 is just the regularizer R from the previous slide. Then how does ADMM work actually? So here I've written it in a graphical diagram, but it's actually the same method as from the previous slide. The server broadcasts its parameter to all the clients. Then what actually turns out, we set the dual variable to the gradient of that loss at the client. We then combine all the dual variables to get a variable here in this dual space, and we communicate that back to the server. And this diagram here gives us the federated ADMM method, where the clients do their local minimization. So the first step is a minimization of that Lagrangian here in theta k. So each client minimizes the Lagrangian, and we add a proximal term to it. Then the second step is doing a gradient ascent on the Lagrangian because we want to maximize with respect to the Lagrange multiplier. And then the server step, again, is a minimization of that Lagrangian in the server variable theta bar, which takes the closed form solution from the previous slide, which is a mean of the client variables plus summing up the dual variables, where alpha is determined through rho. And
this one is too much in place 1 and 2.
Sorry?
It has to be the same row.
It does not need to be the same row. And in practice, we actually found that it gives better results if the row is different. But here for the theory, we use the same row. Yes, good question. And maybe to make the point again, that at a fixed point of this algorithm, all these variables satisfy here this loop diagram. So how do we generalize now ADMM to the Bayesian setting? We lift our original optimization problem. So this is this kind of hypothetical optimization problem if all data was at the same place, where we would minimize all the loss functions LK. But now we consider a variational Bayesian formulation of that global problem, and we consider exponential family approximations for our posterior distribution. And then for this lifted problem, we can simply write an analogous Lagrangian, where now instead of theta bar and theta 1 to k, we have mu bar and mu 1 to k, and our Lagrange multipliers v hat, I call them lambda hat. And then we have, again, here a constraint between our mu variables. So these are the expectation parameters of the exponential family. We have a constraint which ensures that all the exponential families at the client are equal to the exponential family at the server. We have our global regularizer. This was the L0 before, and we have expected losses for the clients. And then we can generalize the structure that we've seen before to that mu coordinate system, where again we follow the same principle that the server broadcasts its parameters to the clients do the optimization to get the Lagrange multipliers, we can combine them to end up at the server. However, the big difference here is that now we have actually, in this setting, we use the dual coordinate system of the exponential family, which was not visible for the standard ADMM case, where the sum of the dual variables was simply added to the server's parameter. Somehow both were in RP, so they were both in the Euclidean space, so this duality was actually not visible in the case of the ADMM. If we generalize it to the exponential family case, we actually have to map from the lambda parameter back to the mu space using a dual map of the exponential family. And the gradients here are replaced by natural gradients, which gives us the side functions also mentioned in the previous talk. So this is an extension of the dual structure that we can see in ADMM to the setting of exponential families.
The important thing is that the lambda hats are added to get the lambda. And this is actually the equation. It's another way to write Bayes' rule. That the natural parameters are natural gradients.
Oh, I see. Right. So in this particular case, right? Yeah. So the global thing is additive, right, of the local things.
Yes.
Okay. Yeah, you do.
And we do the addition in the space where addition makes sense, which is in the lambda space, because addition in the mu space wouldn't make so much sense.
Yeah. So the bottom line is basically multiplication of lots of distribution exponential family. So it leads to addition of the natural parameters. Right, and lambda hat is natural parameter of each distribution, and those natural parameters are individual natural gradients, and they're all added to get the global thing. And you repeat this. Sorry to.
No. So it's a good explanation.
It's Bayes' rule is what I wanted to say.
Yes.
Bayes' rule written in the dual form, so that's why it's Bayes-Duality, and it's just natural.
Okay, so then if we put them next to each other, the two methods, so left is the federated ADMM method from the 1970s, goes back to the 1970s, and now we propose a method, and I believe it's new. So there has been a lot of research since then, 55 years of research on ADMM, so I was surprised to find something which is new. And the changes we make to federated ADMM are these red parts. Instead of just having the loss function here, we take the expected loss. Instead of having this Lagrange multiplier V with theta, we have now lambda hat with T of theta. So that's a interesting looking inner product, which brings the parameter theta to this higher dimensional space using this map T, and the Euclidean distance is replaced with KL. Then the dual update looks the same, but crucially it's here in this lambda coordinate system. And there's existing methods of ADMM, Bregman ADMM methods, which would use another coordinate system here. They would use the mu coordinate system. And that's why this method is new, because we realized it's a very natural thing in the dual update to switch to the dual coordinate system, because these lambda parameters are actually Lagrange multipliers in the exponential family. So it makes a lot of sense to swap here to the dual coordinate system. And also this allows us to preserve the structure. So if you take the mu parameters here, you will not recover here the natural gradients. So this is the crucial step why this method is new, is equation 2, it uses lambda instead of mu. So there's Bregman ADMM, which would use mu, but this is a bad idea.
Addition subtraction should be in the lambda space, is the Bayesian principle. So Bregman ADMM does not do that, right?
Yes.
So if you subtract mu's, it's a different thing.
So the Bregman ADMM
is not on executive. Sorry, I'm speaking without the.
So Bregman ADMM, it still uses copy variables, right? So
yes.
So both are new, but one is the copy of the other. Is that it?
Yes. So Bregman ADMM was proposed for general Bregman divergences, but exponential KL of exponential family is always a Bregman divergence. So there's some.
Because in data and construction, the updating line 2 still involves dual variables, right?
Yes, but their dual variables, yes, they would have dual variables, but they would use the primal variable here. They would subtract the primal variables.
Oh. Okay.
Yeah, yeah. But here our primal variables are mu, but we are not using mu. We are actually dualizing mu. So this would be using the kind of the Legendre function that creates the Bregman divergence, the gradient of that to map.
So it's like some kind of mirror descent in that update.
It's not, the funny thing. It's also not mirror descent, but it's similar to mirror descent. It's some mirror descent-like thing. But I searched a lot. I went into very obscure papers from long ago, and I think this is really new. So
but there is one thing I didn't understand. So this Bayes ADMM, is it still ADMM derived for the probabilistic formulation that we have, using something different than the L2 horizon?
It's a new algorithm which targets the lifted formulation.
Okay.
It's not a standard application of existing ADMM methods to that formulation. This is what people have done in the past. They just black box applied the existing stuff to that problem, but it's a new algorithm that targets this problem.
So you came up with the algorithm and then you proved that it works.
Yes.
Can I ask a follow-up question? So are you gonna tell us under some settings, like, settings of priors, cubes, or whatever, some choices in the Bayesian ADMM where I get exactly the original ADMM?
Yes.
Okay, all right. Cool, nice.
It's the next slide.
No, question is exactly the same question.
Okay.
So we have now this exponential family, and we have many choices. And if we pick the Gaussian distribution with fixed covariance, we exactly recover ADMM. Interestingly, if we pick a Gaussian distribution with a non-identity covariance, but also still fixed, we get the preconditioned ADMM, which is also what people do. And they often have an issue because it's not so clear how to pick the preconditional. But if you're Bayesian, then we can also say we pick a more flexible family where we have the preconditioner free, like a Gaussian with diagonal covariance or a Gaussian with full covariance. And this gives new variants of ADMM that haven't existed before, that have like adaptive diagonal preconditioning like in Adam, or adaptive full preconditioning like in Newton's method. And this is just the beginning for Gaussians. We haven't actually explored it, but different choices of exponential family allows us to design new ADMM algorithms here. And if we run this Newton ADMM on a federated linear regression problem, we see that the Bayesian ADMM converges in a single iteration to the global minimum, because we essentially, the full Gaussian can communicate the full information. But if you would run the regular ADMM or the Bregmann ADMM, one would need many communication rounds to converge to the minimum. So this is a nice property that our method can converge in a single iteration if the loss function of the problem matches the shape of my distribution. We also studied the connection of the method to existing algorithms. So here's our Bayesian ADMM, and I've highlighted the differences to the method from Siddharth's talk in red. So the partitioned variational inference, it wouldn't have a row in front of the KL here. So that's one difference. And as Andre also pointed out, the server update in partitioned variational inference didn't match the ADMM server update. So we have a modified server update. And so these are the two differences, the server update and the row in front of the KL. And what we found actually is that PVI, if one would add a row in front of the KL, it's similar to another algorithm from the literature from the 90s, which is called the alternating minimization algorithm, AMA, but it's not ADMM. And finally, the server update of ADMM is similar to the Bayesian learning rule, with the difference that instead of using lambda here in the Bayesian learning rule, we use a 1 over k of the sum of the client's lambdas. And instead of evaluating the natural gradient at the current lambda, we evaluate the natural gradient at the current mu k. So one can view Bayes ADMM also as a distributed version of the Bayesian learning rule, where we evaluate the gradients at different equations at different locations. And now we also compared this. This is on Bayesian logistic regression. And we found that the Bayesian ADMM converges faster than PVI, either with, if we don't use damping, it just diverges. PVI with damping is a bit slower than Bayesian ADMM. And Bregmann ADMM here was actually quite terrible. So the formulation seems to be important. This is MNIST logistic regression. And we did logistic regression here because we wanted to verify also that it reaches the global minimum. It's not plotted here, but I think in the paper we have a horizontal dashed line. We can see that the method indeed converges to the minimum. So we don't have a convergence proof of that method yet. We can only prove that for certain function it converges in a single round. So for this we have a proof, but in the general setting we don't have a proof yet, but in practice we always observed convergence. Then we also propose a practical deep learning implementation of that Bayesian ADMM method, where we use the IVON optimizer to solve that subproblem, that variational subproblem. And compared to implementing federated ADMM, we actually have to only make the changes in red. So we have one additional Lagrange multiplier update. We have one additional server update for the precision. And we have also in our local training a second Lagrange multiplier, which is quadratic. So this I find very funny as an optimization problem, that typically I learned Lagrange multipliers are always linear. Now we have a quadratic Lagrange multiplier, which I find very intriguing. And that relates also to augmented Lagrangian methods and so on, but I will not go into it. And crucially also here, this proximal term, it's weighted by the precision. So this is like a preconditioned ADMM where we learn actually the preconditioner S through, so IVON's training of this loss function will give you the SK and the MK, and then yeah, we do this. So this is the algorithm that we eventually evaluate on our benchmarks. And we found it to compare quite well to the baselines and also to the method of the previous talk. So there's a lot to digest here. So there's federated averaging, federated prox, and federated DIN. So these are classical methods. Federated DIN is like the best performing federated ADMM method. Then there's federated Laplace from the previous talk, and federated Laplace with covariance, with second order Laplace approximation. And we can see that FedLab from the previous talk actually outperforms these previous methods in terms of test accuracy after 25, 50, and 100 rounds, and also in terms of test NLL. And then here we have Bayes ADMM implemented using IVON, either evaluated at the server's mean or using some Bayesian model averaging. And we can see that, okay, at 25 communication rounds here, it was a bit slow at the beginning, but then eventually it went to a better accuracy than the Laplace method. And additionally, this FedLab-CoF method has quite the overhead because one has to compute these expensive Laplace approximations, which we don't need because we directly get the uncertainty when training with IVON. And then also on larger models and data sets, actually the FedLab-CoF method, we couldn't run it because it was too expensive. But the Bayes ADMM with IVON has actually almost the same cost as the federated averaging or federated prox method. And there we found it could give quite large improvements in the test accuracy. And these are very heterogeneous splits of the problem data to emphasize the benefit of uncertainty. And similarly, we also ran it on a setup with 100 clients where the conclusion is similar, that the federated Laplace and federated Laplace-CoF is better than the baselines. But then using the Bayes ADMM with IVON further improved on top of the federated Laplace methods. Here also in terms of test loss, which indicates calibration. So yeah, that is all. Thank you very much.
The question, do you need to communicate more in each round? And second, do you have any knowledge if you're basically sharing more information with the server, in the sense that the server could actually learn more about the data? Because now we have about distributions, and if you're concerned about data sharing, is that a problem?
So we are communicating more the uncertainties basically. So this additional, we communicate this additional S vector and this additional U vector. So it's more communication than the standard federated ADMM, and this allows us to get the better results because we are sharing more information, we can converge faster, and it becomes especially visible here. This is essentially why we can converge in a single communication round, because we're communicating the whole information about the whole loss function. So it's basically sending the whole loss, the client is sending the whole loss function to the server, and the server could reconstruct all the data examples from what is communicated. Yeah.
Not the individual examples.
Yeah.
Sending sufficient statistics.
Yeah, it's sending the loss function. So somehow one could perhaps reverse engineer it. It's because here the focus was not on the privacy or security, it was purely on the quality and the optimization speed.
So I was just curious that instead of using failure average and all the modifications that you proposed, whether it would be possible to use the modern merging approach that you proposed using the gradient mismatch, because I always feel like the federated thing is more like a natural application of modern merging that just.
Very good question. So if you set the Lagrange multipliers to 0, then this is model merging. This is doing model merging. Basically, the sum terms disappear, and then this S times M, and then you divide by S bar, which is the sum of S. This will end up being model merging, iterated model merging.
And the line 4, the first two terms of the line 4 are gradient mismatch. I don't know if you see it. But if you see VK to be the negative gradient, it's the linear surrogate that I showed in my talk. So LK minus theta transpose expectation of the gradient. It's exactly the correction term. So this is correction term. So it is minimizing gradient mismatch at every gradient.
And maybe on top of it, so I believe that this should work when there is this synchronous connection, and maybe during the asynchronous connection, do you think like the order in which we merge the model matters?
We haven't thought about the asynchronous setting.
Can you maybe explain what this means?
Yeah, so the asynchronous setting would be basically once the client has finished training, it just sends its information to the server, and then the server. The question is, the server could wait until it gets all the information from all the clients and then do the step. Then it's basically that's the synchronous version, but maybe it doesn't want to wait and do the step with the old information from the other clients. And typically the ADMM methods are robust to these things. So there's asynchronous ADMM methods, and my hunch would be that because this is essentially an ADMM-like method, it would also work, but we haven't tried it out.
Okay, so yeah, thank you for coming to my talk. My name is Kenichi Bannai, and I'm leader of the math team at RIKEN AIP. And this conference is for the CREST, but also it's, as MT said, it's the 10th year of AIP, and we're supposed to present a little bit of research achievements of each team. Here? Okay, thank you. So I'll first start. So the plan today is that I'll talk a little bit about the research achievement of the math team, or explain to you what the math team is, introduce you. Then one member of the math team, Akinori Tanaka, is here, so maybe he'll talk about 5 minutes about his work. Then I'll talk about the CREST project, the lead group update rule that we've been doing with MT's team. And one recent application is this work with Keigo Nishida of the MT team on log normal multiplicative dynamics. So he'll give the last 10 minutes about his work. So that is the plan for today. And so first, self-introduction. As I said, I'm Kenichi Bannai, and my specialty is arithmetic geometry in pure mathematics. And I do various realization pod logarithms, special values of Hasse-Weil functions, and block variance and Cotton conjectures. And really, I'm still a pure mathematician, and I don't really do machine learning things. So I don't always feel unworthy to give talks at the machine learning conference, but here we go. And why am I here? So what is RIKEN? So RIKEN is a research institute dedicated to fundamental research in the natural sciences. It's a very important research center in Japan, very famous for physics and chemistry, and more recently in engineering, informatics, and mathematics. And it was founded in 1917, and it started as so it really did many things with companies. So they found vitamins and sold vitamin pills and wakame and food and copy machines. And so they really could afford lots and lots of money, and then they could pour it into pure research. So before World War II, it was really a paradise for researchers because they had really money to do whatever they wanted. But unfortunately, during World War II, they did something with nuclear things. So after the Americans said that we should disband RIKEN, so now the company part and the research part is totally different. And the first director of RIKEN in 1917 was Dairoku Kikuchi, and he was a pure mathematician. Unfortunately, he died 1 year. And afterwards, there were no pure mathematicians for 99 years. And Professor Amari was a director of BSI for a while, so there was applied mathematicians, but no pure mathematicians. This all changed in 2016 when ITEMS and AIP, these are two centers that were created where mathematicians were here. So I'm really the first pure mathematician in 99 years to be part of RIKEN. And how did I become part of RIKEN? So in 2016, I had no experience except pure mathematics. I didn't know anything about machine learning. But Masashi Sugiyama, director of AIP, came to me and says, please organize a team of mathematicians to achieve a breakthrough in AI. I was okay, but you're asking a number theorist, you're asking the wrong person. I was very sure, but he said, no. Behind each breakthrough, a mathematical theory, I mean statistical inference, statistics, optimization, manifold theory. And he asked me, do you know what arithmetic geometry can do for machine learning? And I said, no. And that's exactly the point, he said, because if it's a new idea, then there must be a breakthrough. And at first I thought, what is he talking about? But I think this was very smart, because if I went to some mathematician and says, why don't you join AIP? They'll say, no, my mathematical field has nothing to do with AIP. But I can say, but surely it's more related than number theory. And they'll say yes, and lots of strong people came. So it was really a good strategy in certain sense. And the block balancing cutoff conjecture that I've always been studying, it's a theorem in pure mathematics, but it's a very, very hard abstract theory. So you really needed lots and lots and lots of mathematical theories. So I was good at combining many, many mathematical theories. So it's really the same. If you have machine learning, and it's not one theory you need many, many, many theories, and you want to combine these together. So I was doing the same thing on a different topic, so it's very nice. And our approach was that, so one mathematician of one single field cannot do too much, but if we can collaborate to get the wider mathematical community into this research, then we can do many, many things, and that's what I've been trying to do. So from 2016, we had many postdocs from many different areas on pure mathematics, and yeah, they became very interested in machine learning things. And after a while, they were able to get academic positions, mainly in Japan. So one of the achievements of our team is not the mathematical result itself, but really having pure mathematicians come into the field of machine learning and to start research in that way. So research scientists, SPDRs, junior research associates, and research part-timers. So they were pure mathematicians with training, but many are now in informatics and machine learning. So that, I think, is mainly the achievements. Current member is in this list. Today, Akinori Tanaka, Tomita, and Kei Hagihara-san, and Misato Ogawa-san is here. So if you're interested in mathematicians, please talk to them. Okay. And one thing we have been doing is these retreats where we get machine learning people and mathematicians to stay in one place for 2 nights and talk about these things. Okay. Okay. And then we had many collaborations over the years with Fujitsu's, with Sugiyama team, also Takeda team, Suzuki team, Hayano team. And one big collaboration was with Kawahara team on operator theoretic data analysis. So this was a big CREST project from 2019 to 2024, and it ended March of this year. And the other big project, our main project right now, is with Emtiyaz CREST. And I'll talk about it, but first I'll have Akinori-san introduce yourself. Yeah.
So thank you very much. And this is just an introduction of myself. So as Bannai-san introduced, I'm now senior, not senior, this senior research scientist. I'm sorry. Scientist in RIKEN AIP. And actually, I have a concurrent position in items, Bannai-san says, and visiting researcher at Keio University. And my background is actually theoretical physics, and so that includes quantum mechanics, particle physics, symmetry, string theory, blah, blah, blah. But I switched my research, I guess 7 years ago or something like that, and to the machine learning and deep learning. And in particular, I'm interested in the generative models and reinforcement learning. And I have a GitHub account, so if you are interested in, please look at. Yes, and these are recent papers, and actually it's submitted to some machine learning conferences or the journal in physics. So, and let me quickly review one of them. This third one, the title is Understanding Diffusion Models by Feynman's Path Integral. And I'm sorry, it's a little bit difficult to see, but in this paper, we propose some equivalence between the description of the diffusion models and quantum, one of the machinery of the quantum mechanics called the path integral, and we reformulate everything by making use of the language of the quantum mechanics, and we derive new formula of the likelihood in diffusion model. That's the paper we did. Yes. And yes, and actually, I did not present that work, but in this in this workshop, I present some poster, and in that poster, this is not a presentation of my work, but I just introduced the general concept of the duality in statistical mechanics. And this is a summary of this statement that in statistical mechanics, the duality means kind of correspondence between two different probability distributions. So if you are interested in that kind of topic, please visit my poster. Yes, that's all. I'm sorry, it's just 2 minutes. So. Okay. Yes.
Okay, and then, okay, so a little bit about the CREST project we're doing. So the CREST project that MT introduced, so I am one of the co-PIs. But I first wanted, so talking about Bayesian learning, I sort of want to explain why this project is really, really exciting for me as a pure mathematician. Maybe you'll know everything that I explained, but I want to convey why it's meaningful for a mathematician. And so mathematics and the real world. So mathematics, we have axioms, things that we assume to be true. And then we use deductive logic to prove theorems. So like in the classical Euclidean geometry, you assume things like if you have 2 points, then there should be a line in between. And then if there's any circle, you can choose any center and any radius, and there should be a circle. And you choose rules. And then from these rules, use deductive logic to get theorems, Euclidean geometry. And so in mathematics, it's important that you have rules that are absolutely correct. And if you have these rules, then you try to find the least number of rules, the axioms, to prove many things. So if you want to prove something like a number times 0 is 0, you don't assume it. You don't need to assume it. If 0 is the identity, then 0 plus 0 is 0. That's the definition of identity. So if you use distribution law, then you can prove that 8 times 0 is 8 times 0 plus 8 times 0. And if you subtract 8 times 0 from both sides, you can prove that 8 times 0 is 0. So even simple things in mathematics, you can prove from very simple rules. And that's how we think about the world, how it should be. Unfortunately, the real world, there are no axioms, just lots and lots and lots of observations. And so as a mathematician, starting to work in machine learning, I was like, there's just observations. There's no absolute truth. How are you going to do mathematics? It's impossible. And that's how I felt. I mean, even the real numbers, it's not real. I mean, you have axioms to say that these things exist, but you cannot prove that real numbers really exist. And so that was a dilemma I faced. But then talking with MT, I mean, he has a conviction that is almost like a mathematician, axioms of mathematicians. And then he introduced me to this books by Jane, Probability Theory, The Logic of Science. Then sort of this helped me to understand many things. And so what did Jane say in this book? So it was published posthumously. So the book is published in 2003, but it's based on his notes, which is much earlier, and many of his philosophies. So what is deductive logic in mathematics? So if P is true and P implies Q is true, then Q is true. And this is the logic that we use in mathematics. And so can one say something about P? So if P and Q is true, and if Q is true, then can one say something about P? And I think in math class, if you said P implies Q, Q is true, and if you said something about P, then from deductive logic, you cannot say anything. And if you said that you can, then you get a bad grade. But in real life, if it's raining, then people use umbrellas. Maybe not in England or in Germany, but in Japan, if you get wet, it's really miserable. So in Japan, if it's raining, people use umbrellas. But then if you want to know if it's raining, you're inside and you look out and you see people using umbrellas, then you sort of deduce that maybe it's raining. And so in real life, people use a kind of logic that isn't deductive logic. And so what James says is that, oh, this is an example of probabilistic inference. In deductive logic, you have false is 0, true is 1. It's very absolute. But replace these zeros and 1 by real number plausibility to be a spectrum of the real numbers. Then, if you assume a certain very few laws that reflect human thinking, then from these very small number of rules, then you can prove things like addition. If A is true and not A is true, the sum should be 1. Or like conditional expectation type things. And to normalize this conditional expectation, you don't assume in the beginning that plausibility is from 0 to 1. You assume that it's a real number and it's more plausible if it's bigger or smaller. But if you assume certain rules, then you can prove that you can normalize so the number is 0 to 1. So what I'm saying, what I'm saying is that what was surprising for me was that I thought these probabilistic rules were rules that you assume at the beginning as axioms. But what Jane was saying was, if you use human intuition, then you can derive these axioms from human intuitions. And that was for me surprising because Jane was saying, and from this, you can prove many of the things like hypothesis testing or many of the statistical tools. You can derive plausibility of these things from these very basic things. So at first, I thought you cannot model the world, and it's true you cannot model the world. But there's a way to understand the world using very small rules. And then you can say, based on these rules, you can deduce these things. If you don't believe in the rules, then maybe it means nothing to you. But I think from these small rules, you can do things. And that was very interesting for me. And from that, the Bayes rule is derived. So it's not a rule that you assume, it's derived from that thing. And then from this, you can infer that if it's raining, people use umbrellas. So if this is true, then that should be 1. So the Bayes rule gives this formula. So you can deduce that if it's people are using umbrellas, how plausible it's raining from the other information. And so, yeah, this how to view the world. So before I thought there should be axiom of the world, there should be a universal law. But from this viewpoint, it means that what is the best deduction you can from what you know, the data you have? And then that is a very answerable question because you don't have to worry about what you don't know. You just have to know about what you know and then derive the best answer from there. And from that viewpoint, then I think it's very possible to do mathematical things. So that is why I was really, really excited about this Bayes-Duality. So that's why I'm excited about this.
What is the X here?
X is some hypothesis about the world that you assume. So one thing about probability is you always have a condition for the probability, and the condition imposed is X. And how to choose the prior, I know it's a very controversial question maybe, but you can always say based on this prior, I think this. So, okay. And so this in the Bayesian setting, and so that's the big picture. And then I want to talk about the Lie group update rule in the remaining time. So as you know, supervised learning is finding the best parameter to describe your data. And then Bayesian learning, it came up many times. It's not finding the best parameter, but find the best distribution on the parameters such that the loss minus the entropy should be low. And the entropy is the larger the entropy means you assume less. And so, that fits in with the Bayesian philosophy. And then, as MT pointed out, if you solve it, you can solve it exactly as a product. So it fits very nicely with the Bayes rule. So the more information you have, the more you learn. But what are the update rules? So the initial discussion began with Thomas and Mehmet from our team. Then MT joined and Koichi Tojo-san joined, and more recently Nishida-san joined, and there were other people in the discussion. So what is approximate Bayes? So you cannot, it's hard to do everything on all the probability space. So you take a suitable good family and try to find the best solution in there, and then find the best solution there. And so one example is taking some exponential family and then finding the best one in that exponential family. So if you have a statistical manifold with all the probability measures, it's trying to find the best one which approximates the best solution. And this probability statistical manifold, you have the Fisher metric. So you have a metric space and you do gradient descent. And mathematical gradient descent is like this. You find the tangent lines and you go into the least direction like this. But there are many components. When taking the differential, you're taking the cotangent and you have to remove the dx. So you have to go from cotangent to tangent. Then you're adding something, but the tangent is on the tangent space, but the parameter is on the space itself. So mathematically, there are identifications, but it gets a little bit confusing. But in any case, the update rule is like a gradient descent on the Riemannian manifold or the statistical manifold. And so this update rule, but there are many problems, is how to interpret tangent vector as a point on the original manifold. And permutation via the groups helps to solve these problems. So it's the problem of finding better parameterization of the statistical manifold. So a Lie group is a mathematical object with a differential structure and a binary operation like addition or multiplication. And if you have these things, and if you parameterize, then we found that these are very helpful. In the sense that for Lie groups, you have a thing called the exponential map, where a vector in the tangent space naturally drops to the Lie group. So the problem of tangent space going off the line is solved in many cases. Then because you have the operation, you can construct very general update rules. And so for certain Lie groups, additive, multiplicative, and affine, we can use this parameterization to get Bayesian learning rule update rules. And so Thomas and Mehmet and MT published this in AI Stats in 2023. More recently, we were thinking about what type of exponential families does this whole theory work on? And it's given by the harmonic exponential families, given very generally like this. And the big picture is like this. The generalization is like, so what are the good update rule where the reparameterizations work in MT's theory? Reparameterization meaning that lambda variable goes to mu variable. That was the big point in MT's thing. So what is the general framework that works? And it's given by this harmonic exponential family, which is very nice. So this is a general framework to do Bayesian update rule. And the big question is, so there's a good mathematical theory. So what? And the so what part is probably Nishida-san's talk, where he will apply this to, in the case of the multiple group case. So Nishida-san, yeah, where are you? Yeah. Okay.
Okay, so today I will talk about some log-normal multiplicative dynamics for stable operation training on large networks. It's a collaboration of the some math teams and Thomas and MTs. This paper is out this Tuesdays. So I just briefly introduce these papers. So maybe some people know this new NVIDIA's computers. This is like NVIDIA says great new architecture like supercomputer all your desks. So they say, so this is a supercomputer. I don't know what is the definition of the supercomputers, but so they explain that. So it only has this computer has 128 gigabytes of the memory. It's not so enough, but so after that, they say developers can prototype, fine-tune, and inference the latest generation of reasoning AI model from DeepSeek, so up to 200 billion parameters locally. So this is very strange things. So maybe it hides some of the torics is this. So what is the torics on new supercomputers? So this is next generation NVIDIA's GPUs some technologies, and maybe we can use like a few months later. So they say like 5th generation of the tensor core engines. So using a new precision data formats, like they can use a compact data formats, like 4-bit or 6-bit floating points. Then why is it very important? So we can focus on this here. So this new architecture derived 30 times speed ups compared to the previous NVIDIA Hopper GPUs. So that Hopper means like a H100 to H200. So very late, so most very high performance GPUs. But if we use, of course, it's not only the data formatting issues, but it very strongly contribute to the speeding ups of the new AI chips. So yeah, very important, so essential for the next generation AI hardware to use low precision data formattings. So the low precision is some case in biological aspects, some neuroscientists say, oh, synapse have only few bits, like especially some researchers say synapse have less than 5 bits, and that synapse have some distributed follow log normal distributions. So why it's occurred from why so log normal distributed? Some also neuroscientists think about interpreting sampling fragmentation must be like multiplicatively. So it will largely lead to the log normal distributions. Also, some machine learning researchers are also very interested in, if we choose like idea of the biological synaptic some log normally distributed things. Okay, they try to apply the multiplicative weight updates rules. So some people, it's for the purpose of to use the low precision data formats. Maybe these biological synapse ideas help to next generation AI chips usage. But so of course, some of the multiplicative updates seem to be promising for energy and efficient low precision ANNs. So some people and a lot of hardware researchers try to development, but it's not so much. That is not common to use log normally distributed things because that is not succeeded for large neural networks such as vision transformers or like GPT-2 things. So the lack of the vision, so usually a lot of the paper or use additive weights, but in low precision data formats, it's occurs from like rounding issues. If this red line is a represented value, so this value gets gaps that increase approximately property. So if the weight is very small, it's pattern-based with small range, it works. But if once the weight is very large values, you add to the Gaussian noise, it's not make sense. So because it's for that reason of the rounding issue may lead to no noise injections. It doesn't work so much well. And previous research is use a multiplicative update is also they maybe take care of the rounding error issues, but they don't care about some noise injections. So noise injection is also needed to the proportional to the parameter values. So if change some SDD standard deviation for each parameter's mean values, so it's very makes sense to the some overcome the rounding errors. So then what we want to try to the log normally distributed weight things for update and noise injection. We need a good theories. Then it's a very nice theory. We can assume the weights, assume the log normal weights. So regroup BR so suggests like can use a log normal distribution for weights, use a log normal weight noise injection, multiplicative group of the positive layers. So this is a simple algorithm of the Lie group BRs. So for log normal distribution, once you try to use a sampling from the log normal noise and multiply the parameter, this M is actually the median of the log normal distributions. Then after that, you compute gradient, compute momentums. After that, you apply the multiplicative updates. So Lie group, if we use a log normal weight distribution use Lie group BR, you can naturally use noise multiplicative noise injection and multiplicative updates. So, but it's very hard to optimize large neural networks. So I try to fix some of the previous research, like maybe engineering aspects. So the main idea is very simple, to apply the Lion optimizer. So it means like decoupling. So if you compute a gradient, but previous gradients is including some regularization terms, but in your case, decoupling such terms and use double of momentum values and apply for the sign operation for some temporary momentum values. After that, and we assume the prior as a log normal distributions. Finally, so we get some LMD update rules. Of course, this is a multiplicative update, but if we assume the log normal prior, it makes some multiplicative weight decays. Then this proposal methods is including multiplicative noise injection and multiplicative weight update, also multiplicative weight decay things. So a lot of multiplicatively regularization techniques is there. No?
Very multiplicative.
Okay. Sorry. Okay. Then we now, so I try to use emulation because of I don't have any 2 months later we can use a GPU register version of GPUs, but I don't have that. So I use quantization emulate of the floating point 6-bit of matrix multiplication. So and multiplication flows, and also use like parameter samplings. So its multiplicative updates cannot change the sign of the weights. Then we need to use double of the parameters to divide. In this formula, it can use switching signed weight. So we all in our experiment use low precision matrix multiplication for neural network training. Use neural network training, but only forward. Backward is I use the bfloat 16th. But inference is very important for accelerate some more inference things. So this is a result of the vision full scratch training of the vision transformer on ImageNet. So this is a result of the baseline of the ADMMs. Our proposed methods is very good performance, and the baseline of the so basic multiplicative update rule is done so much works. And next, we try to the training full scratch training or GPT-2s, or also some previous multiplicative ADAM, it doesn't works. And so final score is very similar to ADAM-Ws, but forwarding low precision forwardings, ADAM-W is performance is very degraded. But so our proposed multiplicative dynamics update rule can get the same same convergence of the results. So that is so LLD is achieves like better performance rather than the ADAM-Ws on the vision transformer with the ImageNet and GPT-2 on open web text. And also some case, a lot of the research shows multiplicative updates tend to exponentially growth of the weights. So then we check some weight norms of the weight norms. So then Madam is very strongly large, very large value of the norms, but LMD is very not so much large values. So it suggests like this multiplicative noise injection lead to the very strong regularization for the trainings. Then okay, anyway, okay then. After that, so then we introduced a multiplicative noise injection. How important it is? So the result is sampling is multiplicative sampling is very important for the low precision trainings. This is the results of the vision transformers. Then this red line is floating point forwarding computing with no sampling. So we use a parameter of the mean values, only no noise injections. Then this green is noise injected trainings. So this figure means weight norm. So this suggests that if you don't use a noise injected sampling and no use of the samplings, it may very easily to increase weight norms. That means a little bit overfitting or underfitting. So more worse scores. But if you use noise injections, it gets more better performance. So applying multiplicative noise can mitigate the negative effects of the low precision operations. So yeah, that's all my short presentations. But anyway, so yeah, the next generation that use also low precision data format in AI hardware is becoming increasingly important. And the optimizer need to be adapted to these new data formats. So that case, so our proposal methods MD introduce not only multiplicative weight updates, but also multiplicative noise injection and the weight penalties. So that may lead to the using low precision data format matrix multiplications. So this methods achieve efficient training of the large-scale networks like vision transformer and the GPT models. So I hope its model makes next AI eras of the hardware. I hope this algorithms is a next standard of the low precision trainings of optimizers. That's all.
Yeah, this one is for Kenichi-san, if you will. So I really appreciated I find the lead group stuff really beautiful, right? Because you're like, what do you need to do Bayesian learning, right? And so you need the additive structure in the sense that your approximation, it can be sort of added piece by piece from information. Right. And then you need the sort of the differential, i.e. the gradient part, you need gradients doing this, so that you can go and iteratively find your solution, right? So your approximation. So that's and then if you parameterize this with a lead group, it gives you both those things very nicely together, which is really beautiful. Right?
Up until that, that's general, but in Emtiyaz's thing, the reparameterization going from lambda to mu is very important.
Yes, and right. And then it also gives you that preserved duality.
Yeah, that I think finding what works for that is, I think, important in our work.
So this like particular formalization from math gives you these three really nice things.
Right.
So
Yes. Yes.
So I think, I'm just recapping to set up for my real question.
Okay.
The real question is, this is really lovely for a pure mathematician to see something you already do in this new light.
Yes.
Right? So I think, a really interesting question that I'm very curious to hear you say is what is the vision as a mathematician you have for, what are we offering? Right? Or you are, our people are learning by abstraction, right? By formalizing what they already do, right? In a big picture, you've already shown an example, right? But in a sort of big picture way. And sort of maybe the flip side of asking that question is I often find that, the way that machine learning, and there's nothing unusual about this, folks engage with mathematics is this is a tool. right? Again, to compute what we already do.
Right.
Would you say that there is a deeper way that you wish machine learning folks engage with mathematics? Right? So, flip side of the same question.
The first thing is what we're providing sets of distributions which you can use MT's theory. So, I mean, it's not ad hoc. You don't have to try many things. I mean, this is one distribution that should work. And of course, for implementation, there are many, many, many difficulties, but theoretically, it's something to it. So that's what we're providing. So many options, many things you can try. And we don't know if it's good or not, but you can try. And as a mathematician working with MT, the first part is what I really like is that, so you can really justify why it's correct or why it's not correct, depending on the assumptions. So you have certain assumptions about plausibility that you believe in, or if you assume this plausibility theory, then you have the best possible answer, assuming this plausibility. And so you can be really scientific about your algorithms. So you're not saying it works, it looks like it works and it looks good, and so why not? It worked 10,000 times, so it should work the next time. You're not saying that. You're saying that based on these principles that it's working. And I think that kind of understanding about the system is very, very important. And I think we mathematicians are good at logic and building theories that really are consistent. So I think using these certain logics that we can help to make consistent systems or theory.
And coherent also.
Coherent.
Things make sense, no matter in what way you look at them, they all look the same. It's the addition for me.
Right, yeah.
Right.
Really like this question, could you maybe specialize it a little bit more about the question, like how does number theory specifically you think can contribute to this? Because I mean we have probability theory, optimization, numerical analysis, there's all different mathematical theories also in these areas, right? So how is number theory kind of, because this is kind of very novel as an idea also for me.
Okay, so as a number theorist, I think our greatest strength is numbers are very discrete, 0, 1, 2, 3, 4, 5. But traditional number theory is very related to L functions in automorphic forms and very continuous things. So we've spent hundreds of years thinking about the relation between discrete things and continuous things. And continuous things have very good theory. Discrete theory is very hard, but computers are discrete. So I think we have a very good intuition about continuous and discrete that could help really revolutionize this, hopefully. Yeah.
Looking forward to it.
All right, let's move on.
Yeah.
Thank you for the introduction. Today I'm going to talk about my work on improving LoRA with variational learning. And by the way, I'm Bai, and I'm now working part-time in Team ABI, and also I'm from Yokota Sensei's lab. It's in Institute of Science Tokyo. So I'll do a very quick PR time for Yokota lab. So this is Yokota, Prof Yokota View, and what his research is mainly about, I mean, the research topic on our lab is about combining high performance computing with all kinds of themes. For example, in this picture, it's Japanese, but it's essentially saying that they make some artificial, very large image dataset on which you can pre-train your model and get just as good performance as the in-house large datasets in companies like Google. And also they have something like the LLM JPU project, which is amazing because they train a 7 billion model on the Fugaku supercomputer, which has no GPU at all. And also they have the Tokatek project, which is project from our university where they they fine-tune a llama model on English and Japanese dataset, and they achieve very competitive performance in Japanese. Yeah, so this is just our lab. We do high performance computing and deep learning. And so I'll introduce my work. So too long, don't read. We use the IVON optimizer to improve LoRA fine-tuning for large language models. So this is LoRA, and we just simply use IVON to fine-tune the LoRA parameters A and B. Is actually very simple, but the results we think is very good. It can achieve higher accuracy with similar speed. So this shows the gray line here is the ADMM, and the red line is the accuracy of IVON LoRA, and you can see that it can achieve an improvement in 2.9% with just a similar time, wall clock time. And also it achieves better calibrated output. I think maybe as we work on Bayesian methods, maybe you're familiar with the concept of calibration, so I'll just skip this one. And LoRA, I think maybe we are also familiar with this. LoRA is the aberration for lower rank adaptation, where you just fine-tune you don't want to fine-tune the whole model because it is very large. And so you want to use LoRA, which only fine-tunes a small number of parameters. And it inserts these small chainable low rank matrices A and B into the larger frozen pre-trained weight layers W0. And the benefits of LoRA is that it improves the task-specific performance with far fewer additional parameters and also computation. So there are some Bayesian methods trying to improve the LoRA fine-tuning, and I will introduce two here. One is Laplace LoRA. It's just essentially combine Laplace approximation with LoRA. So it try to fit a Gaussian posterior after training finishes, and it's the Gaussian posterior. The M here is trained with ADMM or maybe other optimizers, and the sigma here is in Laplace LoRA they use non-diagonal, specifically K-fact Fisher of M, which is calculated on the training data after training finishes. And they use some technique like model linearization, and yes. So there are some limitations here. For example, you need access to the training data to do this Laplace approximation. You need the K-fact Fisher, which can induce some overhead. And also you need the Jacobian of your language model. So for classification problems with a small number of classes, it will be okay. But in more general settings where you, in the generation task, the number of classes is essentially the vocabulary size, so your Jacobian will be prohibitively large, and it doesn't scale to a more generalized setting. But it still improves the calibration of large language models a lot. And also we have the method called BLOB, which means Bayesian low-rank adaptation by backpropagation, and the main idea is to combine the Bayes by backprop with low-rank adaptation. But they still have introduces a lot of modifications which together they make their method works very well. They only Bayesianize A. They introduce some flip out trick to improve the sampling efficiency. They have some different parametrization. And in our test, actually, the blob method works pretty good, we think. Though I think our method works better, but blob is also a very competitive baseline. So our method, IVON LoRA. again, I think we've already introduced IVON, so maybe you have some feeling about it. We just simply use the IVON optimizer to optimize the LoRA parameters. It's just like this. We optimize A and B, but actually there's one more thing that we conduct the so-called uncertainty guided pruning after training finishes, and we invented this name, the uncertainty guided pruning, but essentially it's just setting some parameters with the largest variance to 0. I have to clarify that the pruning here is not aimed at to reduce the memory usage or to make the computation faster, but we find that this kind of pruning actually improves metrics, including accuracy and calibration. So here it is. First, we find that pruning a small number of LoRA parameters, say 10%, for example, it improves the calibration a lot without affecting accuracy much, and sometimes it can even improve the accuracy. So we conduct experiments on 6 datasets, and if we zoom in here, we show the figure on one dataset. So first, if you draw a vertical line at the prune, the axis at the 10% that position, you can see that the accuracy, which is indicated by the red line, it doesn't change a lot, but the log likelihood indicated by the blue line improved a lot. This is the first thing we find that pruning a small number of LoRA parameters gives benefits. And another thing is that we find that pruning parameters with the largest variance V is better than random pruning. So pruning parameters with largest variance V in this figure is indicated by the curve with the circle mark, and the random pruning is indicated by the triangle mark. And as you can see, the curve with the circle mark always goes above the curves with triangle mark, indicating that the pruning, the UGP we proposed, in which we prune parameters with the largest variance, it consistently works better than random pruning. And this indicates the usefulness of the variance vector V learned with IVON. Okay, so I'll show some results. First, I'll show some results on common sense reasoning datasets. We fine-tuned the Llama 3.23 billion on common sense reasoning datasets. Well, I prepared some to let you know how the dataset looks like, but you can just think of it like some classification problem or multiple choice question answering problem. And we achieve much better accuracy. Maybe we can claim it to be much better. So we compare our method. First, we have the setting where we only use the posterior mean M. So at the test time, you just use the posterior mean and no test time overhead at all. It means these improvements in accuracy, it is free at test time. So in this setting, we compare our method to blob, which can also be evaluated only using the posterior mean and also the standard ADMM training. So our method achieves 1.3% of improvements in accuracy compared with ADMM, and also 0.7 compared with blob at mean. And also, if you can also use the posterior we learned. And for blob and IVON LoRA, it means at test time, you can sample 10 models from your posterior and then average the prediction. And for Laplace approximation, it means you do the model linearization. And the results is saying that in such a maybe more Bayesian setting, both of the Laplace approximation and the blob, it actually degrades the accuracy more or less compared with the ADMM training. But IVON LoRA at such Bayesian setting, it still maintains improvements in accuracy of 1.2% compared with the ADMM training. And also, we achieve better calibration. It is compared with ADMM. Compared with ADMM, it achieves better calibration. It is actually not so as good as blob and Laplace approximation, but actually the comparison is not so fair because the higher the accuracy is, empirically we find it is the difficult to achieve a better calibration. So IVON LoRA actually achieves better accuracy, and empirically we think it is harder for it to achieve the good calibration. But actually, compared with ADMM, it improves calibration a lot, and is only a little bit worse than the blob and the IVON LoRA. And we also have some results on the GSM-8K, which is some task on generation problem, which is we'll try to solve some math problem. And here we fine-tune a QN 2.53 billion model on this dataset. And in this dataset, we have some math questions, and also we have the answer. The answer can be divided into two parts. The first part is like a chain of thinking. We try to solve this problem step by step, and then we have the final answer on which we actually calculate the evaluation metrics, namely the accuracy. So we fine-tune the QN model on this kind of dataset. And another thing we do here is that we do test time computation, which is very popular recently, and essentially, is sampling. We do this to improve performance. And how we can do this? So for ADMM and IVON LoRA, when evaluate at only using the mean. So first we feed the math problem into the fine-tuned large language model, and then we sample outputs from this model. And as you can see, they may have different answers. And then we do a majority voting to get the final answer. But for IVON LoRA, which can learn posterior, the sampling procedure can be a bit different. Say for IVON LoRA, for IVON LoRA, we have the posterior, and first we sample models to get maybe several fine-tuned. We get several sampled models. Then we give this problem to all of these models, and we sample some outputs from all of these models. Then we do majority voting and get the final answer. So we expect that if we use the learned posterior, we can get a more diverse model, and thus more diverse output, which could be beneficial for the performance. And it turns out it's true. So here we compare IVON LoRA with the ADMM baseline. First, for a small number of sample sequences, the results shows that IVON LoRA, at mean, which means only evaluate using the posterior mean, it works the best and achieves some improvements to the ADMM baseline. And what makes us somehow excited is that if we increase the number of sequences or outputs we sampled, IVON LoRA works very well, and as you can see, it leads to a very big gap compared with the ADMM. So it means the sampling from this posterior to first get a lot of models helps with the performance a lot. And to add a comment, the increasing speed of computation is much faster than the increasing speed of the dataset size. So yeah, maybe in the future, this kind of scaling will be another, driving force for the improvement of large language models. And also in this example, again, we show that the pruning helps. And this is the final slide. I think it tries to show that. This is an application study which we show that tweaking this sampling temperature at test time could lead to some improvement in performance. So here is the formula of the posterior variance. It is given by this, and at test time we can actually scaling the variance by using a larger lambda, which is given by tau lambda, and this might further improve the performance. So here we show the result. As you can see, for tau, for example, for tau equals to 5 or 10, the accuracy improves a lot, but we achieve a similarly good calibration. The expected calibration error as the standard sampling procedure where the tau is 1. So this means this can be another trick. If you at test time you tune this hyperparameters a little bit, maybe you can get even better performance. Okay, so I think that's all of my presentation.
All right, thank you very much.
Thank you.